initially Kerala was the role model for all other states
Yeah.
how to reduce the COVID
Yeah,
disease.
she is doing her maximum. We should appreciate, actually.
In spite of
And when the COVID situation is over, please come to our institute, sir. Raghavan
yeah,
sir, Mahadevan sir, Sudhakar Rao sir. Please visit us.
Hello, madam, and everybody.
Babi.
See,
Hello.
the situation, we are only praying that situation should improve. They say it keeps on changing.
Yes.
I really don't know when it is going to. Actually, in Karnataka also, every day they are reporting almost 10,000 cases, with nearly 5,000 from Bangalore itself. So you really scared even to go out anywhere, even for some basic things. So it has become like we hope everything settles down.
Yeah, and someone invents the vaccine.
And then the student community is the worst affected. No, I'm sure they should all be now become free and then get their due, because some of them are so good they are not able to do as good as what they would otherwise do it.
Yeah, good morning, ma'am.
Our students have developed some COVID-related projects and also. Actually, EC department has developed a mask. Computer science department has developed an app that is for helping the shopkeepers. Mechanical department has made a sanitizer model.
That's all very good. That's very good.
Foot operated wash basin. So many things students have done here in Kochi.
That's nice.
Principal madam, you put all these things in Malayalam Manorama or Indian Express. The others people should know about all these good things.
Sir, the problem is our management does not believe in all this. They feel that our students are our brand ambassadors, so they have to stick for us. Yeah.
But
it's true. The public has to know about it.
Sir?
Excuse me, shall we start with the inaugural session? It's 8:40.
Okay.
Okay, so good morning all. It gives me great pleasure to extend to you a very warm welcome on behalf of Department of Electronics of Kochi Institute of Science and Technology to the inaugural ceremony of Phase 3 of AICTE sponsored 6 days short-term training program on the topic Trends and Technologies in Antenna Design and its research scopes. Kochi, an international organization headquartered in the UK, found its inception in Kochi in the early 1970s. The Kochi Institute of Science and Technology (TIST) was founded in the year 2002 and is a leading center for research recognized as Scientific and Industrial Research Organization by Department of Scientific Industrial Research, Government of India. TIST also serves as a K2-approved research center with Param supercomputing access, and it is also recognized as Center for ASAP. TIST is affiliated to APJ Abdul Kalam Technological University, Kerala, with 9 undergraduate programs and 7 postgraduate programs, out of which the computer science engineering, electronics and communication engineering, civil engineering, and mechanical engineering have been re-accredited by the National Board of Accreditation. One of the first departments at TIST, the Electronics and Communication Engineering Wing, was established in the year 2002. Since its inception to this day, the department has stood firm in its objective to impart quality education and training at the undergraduate and postgraduate levels in various areas of electronics and communication engineering. The rapid growth in wireless communication technology demands the design of antennas with necessary features according to the application domain. The STTP, which has been sponsored by the All India Council for Technical Education (AICTE), is primarily intended for faculty members from engineering colleges, industry persons, PhD scholars, and postgraduate students from various institutes. The 6 days short-term training program aims to provide the participants with the latest techniques in antenna design through lecture sessions by experts in the field. Since there are a number of challenges in the design of antennas, this course provides technical talks which entails in-depth and comprehensive knowledge on antennas and its design. If your actions inspire others to dream more, learn more, do more, and become more, you are a leader. Without further ado, let me invite the head of the Department of Electronics, Dr. Deepa Elizabeth George, for the welcome speech.
Good morning to all. Welcome you all to the third and the last phase of the AICTE-sponsored short-term training program on trends and technologies in antenna design and its research scopes. At the outset, we take this opportunity to thank the God Almighty for being able to organize this STTP amidst this pandemic. The management of Turkish always encourages continuing education, and that is the greatest motivation for us in organizing programs of this nature. Today, for this inaugural session, we have with us representing the Turkish management our beloved principal, Dr. Preeti Tekit. She has always been our support and encouragement in all our endeavors. Madam, on behalf of the Department of Electronics, we welcome you to this inaugural session.
Thank you, Deepa.
Today's inaugural session is all the more special as we have with us one of the most senior respected professor of our country, Dr. S. Raghavan Sir from NIT Tiruchirappalli. It is an honor and blessing for us to have a person of his eminence in our midst today. Raghavan Sir has been associated with Turkish for the past 2 months, and he has been our mentor for organizing this 3-phase STTP. Sir, on behalf of the management and staff of Turkish, we extend a hearty welcome to you. We are delighted to have with us for this function our first speaker for this STTP, Dr. Sudhakar Rao, Senior Technical Fellow, Northrop Grumman Aerospace Systems, USA. We consider it as a privilege to have a person of his caliber as a resource person for our STTP. On behalf of the management of Turkish, we extend a hearty welcome to you, sir. We are also fortunate, privileged, and honored to have another senior professor of our country, Professor Mahadevan, sir, who has also joined us for this inaugural session. Sir has been constantly supporting us all through the last 2 phases, and we are very happy that he is with us, supporting and encouraging for this STTP also. Sir, on behalf of the management and the staff of Turkish, we welcome you to this session. I take this opportunity to welcome the coordinator of this STTP, our beloved professor, Dr. Perumal Shankar, and our co-coordinator, Dr. Jnana Sheila, and her team to this inaugural session. Turkish heartily welcomes all the participants to this 6 days AICTE-sponsored STTP. We have tried our best to bring the right blend of experts from industry, research, and academics for this program. We are sure that all of you will enjoy the 6 days training program. We wish all of you a happy learning. Thank you.
Thank you, madam. Encouragement, enthusiasm, excellency is one of the major aspects of an organization. With an object of encouraging the spirit of research and innovations, we can now hear few words from our principal, Dr. Preeti Tekit, who has been a constant support throughout.
Respected Dr. Raghavan sir, Dr. Sudhakar Rao sir, Dr. V. Mahadevan sir, first of all, on behalf of the entire management of TIST, I welcome you to the TIST family. We are really privileged to have such eminent guests here today. And as far as Turkish is concerned, we started in the year 2002, and we have near 8 UG courses and near 6 PG courses and a MBA program, a full-fledged MBA program under KTU. We are also a KTU approved research center, and that is, we have a ASAP program running over here, Advanced Skill Development Center, that is, which gives additional training to students in artificial intelligence and machine learning. And we have a telepresence lab here, which connects the institute to the nearby IT parks. And we have active chapters of IEEE, ISTE, IEE here. And we wish to start a new chapter of robotics and automation also. I'm sure Dr. Sudhakar Rao sir will give us proper guidance in that. And that is, we are planning to have artificial that is planning to start computer science and artificial intelligence in the coming year. That is. We plan to become. We are in the that is our road in our roadmap. We have put actually we are in the way to become autonomous. So that is currently we have been in NBA accredited as well as NAC accredited, and so we are on the way in becoming an autonomous institute. So I wish we will get the eminent guidance of there is all these experts in making us an autonomous institute. So I wish the STTP on antenna design and research scopes for 6 days, third phase, it will go on well. And that is all the faculty here as well as the faculty who are attending from outside also will get an excellent chance to know about the recent researches in this field. And another STTP is also being organized by this department on robotics that is in November. So a lot of initiatives have been taken by the department in doing funded FDPs, then more being selected for conducting STTPs, then getting research fundings, etc. So, and I also thank Dr. Perimal Shankar and Dr. Deepa for taking this much efforts in organizing such programs. So I wish the department all the best. Once again, I thank all our eminent experts who have joined today. That is for this third phase of antenna design and research scope, STTP on antenna design and research scope. Thank you.
Thank you, madam. Imagination tries for improvement, and these, together with proper implementation, makes a dynamic engineer. Today, we have with us a very dynamic engineer, Professor Dr. S. Raghavan, Department of Electronics and Communication Engineering, NIT Trichy. Dr. S. Raghavan is a senior professor in Electronics and Communication Engineering Department, NIT Trichy, and has 33 years of teaching and research experience. His interest includes microwave integrated circuits, RF MEMS, bio-MEMS, metamaterial, and microwave engineering. He has won the Best Teacher Award twice and conferred with Honorary Fellowship of Ancient Sciences and Archaeological Society of India. His first research scholar obtained gold medal for the best thesis of the year. He has to his credit 75 research papers in international journals, 65 in IEEE Explorer, 127 international conferences, 26 national conferences. He has guided more than 8 PhD scholars. He is senior member in more than 20 international and national professional societies, including IEEE, IEI, IETE, CSI, TSI. He has organized various workshops of national importance. He was a president of REC Trichy Faculty Association for 2 years. He made an impact in microwave engineering education among student community at large. I invite Dr. S. Raghavan to say a few words.
Thank you. Highest dignitaries of antenna community of the world, country, and valuable participants. Here is a person who puts the computer on at 8:40 before every FDP and puts it off only after the valedictory function. And she is none other than the head of the department of ECE, Dr. Deepa Elizabeth. And she anchors all 22 persons and main reason for the grand success of the FDPs. And she is given a very free hand by the management guru and the principal, Dr. Preeti Tekat. All are able to do successful events only because of the generosity of worshipful management trust of Takach. And the first and the foremost attractive thing of these 3D FDPs, first of all, star-studded resource persons. Maybe I'll take 2 minutes to tell about them. But the person who brought all those people to the world by the colorful poster is Prakash Mohan. And the person who make this IT connectivity flawless are Joby and Shri Manoj. And first two FDPs were anchored by uh, Dr. Vinu and Sri Lakshmi and their group. And now it has been shifted to another able group headed by Dr. Jnanashila, Professors Roshini, Sajita, Swati, Danya, Deepa Mary, Nishant, Renjit, Girish. And everyone, especially Professor, 3, 4 dignitaries have joined. Those people plus participants, they would have heard some professional voice in the name of comparing. They are not from television center or radio center. They are none other than Sona and Shena. They have been doing every day, whether it is the morning 8 o'clock or evening 4 o'clock, same modulation. They add credit. They make the sleepy people to become a sleepless people by the wonderful shrill voice. They add color to the success of this FDP. Then you might have seen initials for all the persons. Here is a person whose initial was antenna, and that person is no other than the guide of IEEE Fellow of the World, Dr. Sudhakar Rao. Dr. Sudhakar Rao guide, his name was Antenna Narasimhan. Because of him only, he is shining like anything in the world. So that is where everything is in a different uniqueness of this TOH. So we are all fortunate to have such a uh, high authority in antenna of the world. He makes India proud by staying in America. Dr. Sudhakar Rao was one of the first persons to join in today's meeting. He's always punctual as that of Takech. And we have seen different types of antennas in Balanis. And here is a person who has developed all those antennas and got measurements done up to the different standard. And he is none other than Dr. Lakshmana Meru. He is a competent person, or is a contemporary to our already known person, Dr. EMC person of the world, Dr. D.C. Pandey. He is also with us in the inaugural function. The next person, the person who plays with the satellite. We know satellite communication book, but here is a person who played with the satellites like Indrayan, Chandrayan, Mars and all. There is no other than Professor Mahadevan. What books do not tell, he will tell practically. Then there is another person, the youngest IEEE chair APS of Madras chapter, Dr. Shanmuganandam, the one and the only gold medalist of antenna research of NIT Trichy. Fortunately, he was also my student. And Takech is known for many things. Now only we come to know through principal about the new branches. And fortunately, on behalf of all, I once again request our great Dr. Sudhakar Rao. In fact, I am occupying the chair which he is supposed to occupy. Because of the time lag or lead, I got the opportunity, or I feel proud to be the chief guest. There are many more persons who is supposed to occupy my chair. And we wish that Dr. Sudhakar Rao extends all the possible help. And also, I wish we get the help from Dr. Mahadevan, Dr. Lakshmana Meru, and through principal and HOD, I request the management for having done wonderful 3 phases of the FDP, which even IIT could not organize in a single phase. Bring the latest state of the art anechoic chamber and all those things. If Dr. Sudhakar Rao says, or Dr. Lakshmana Meru says, or Dr. Mahadevan say, no one will question. Having inaugurated by the AICT regional director, the tech ECE department is doing everything by exactly at 8:40, the MOC prompted. Not only that, they conduct the test. No person in India conducts test exactly for 30 minutes, not more, not less. Many people allow 1 day for writing the test. So everything, they follow the timings, and that way, that is another uniqueness of the Takech department. And I will stop because I'm afraid of MC, whether she will prompt me. I will take 3-4 minutes. People know the monk, but there's a monk of India for FSS, and he is no other than Dr. Shivanarayanan of NAL. And there is a KO of India, and he is no other than Dr. Mandal. And calamity should not stand in front of the technical ability. The role model for the whole world is nobody other than Dr. R.K. Mishra. His brother, a person who threw the vice chancellor post for ethics, and he is no other than the present director of NITTR, Dr. S.S. Patnaik. Like that, there are another lady person who has established the first chamber of its kind in Karnataka chapter. And there's another person for whom method of movements, method of lines are child play. And his method of teaching will be entirely different. I wish Dr. Sudhakar Rao, Dr. Lakshmana Meru, all people admire the way in which he makes online classes, offline class, just like Blackboard. Is known for that. He is nobody other than Basudev Ghosh. All those things are child play for that. And there are some few young people like Dhundi Kumar, then Jones, many people like that who make the antenna measurements easy. They know the difficulties what young people face in antenna measurements, and these young people have come out with a small domestic devices which make antenna measurements easy. So that way I feel like telling many of the things, but finally this is not the last word. If time permits, I would have named all the people of the ECE department who have brought out real success, what big institutes could not attain. These people have attained. I only wish the great people bring out to the world what this institute of the God's own country has made a miracle in the antenna. Almost all the people are expert and unique experts in the respective one. We had 3 vice chancellors, Dr. Surendra Pal, many directors, all have joined, and only because of Dr. Elizabeth told at the first, because of the God's Almighty's help. It is due to their help and due to the good heart of the people of the ECE department and Takach, including the principal and the worshipful management. Everything came just like a miracle. It is a magical miracle that happened. Finally, I want to tell, for every success of a man, there used to be a woman. But here, for every success of the man, there are 2 women. One is the HOD of ECE, Dr. Deepa Elizabeth, and behind that person, another very great person, Dr. Preeti Thakat, the principal. And in spite of personal constraints, there's a person who has been continuously putting all the efforts to make the 250 participants here the best of the world. And he is nobody other than the RF MEMS specialist, Dr. Perumal Shankar. There are many constraints. Today, there are 2 important things. One for the country, the NEET exam results are going to come. The second thing for IEEE chairman-elect, the person who is likely to get also was my student, Dr. S.K. Ramesh. So in such a important, crucial circumstances, Dr. Perumal Shankar is able to devote a lot of his time, mainly because of the 22 persons of ECE department and other people with the strong support of principal and the management. Definitely the TOH FDP should be written in the golden history of the recent FDPs, and I know that stalwarts will help. Maybe one sentences from Dr. Surendra, Dr. Sudhakar Rao, Dr. Lakshmana Meru, and Professor Mahadevan will add color with the permission of the HOD and principal.
Sure, sir. Sure,
Yes.
sir.
Dr. Sudhakar Rao We are all fortunate because of COVID only. The American settled India, who makes India proud, has come exactly at 8:30, and also Lakshmana Meru. He will show all the antennas to the society, what they have seen in the books only. So I would like to tell about one or two sentences. Dr. Sudhakar Rao sir,
Yeah. Thank you, Professor Raghavan. So you have given a nice speech. So you wanted only one or two lines. So I would say that you're the reason why I'm here. I think you sort of asked me a couple of times. So I couldn't say no. And second reason is Professor Perumal Shankar. So he's such a nice person. And so I cannot say no. I think Kerala is a very nice place. I had been there many times, and people are very humble, down to earth, and very nice people. So I would like to visit sometime. TOH, and thanks Professor Deepa and Professor Preeti Taka for organizing this. And I think you have wonderful speakers here. So I think it's we'll leave it up to the teachers and students to hear what people have to say. So I'll stop at that point, and thanks again for inviting me.
Thank you, sir.
Dr. Lakshmana Meru.
Good morning, everybody. Dr. Raghavan, Dr. Preeti Tekat, Professor Dr. Deepa Elizabeth George, Dr. Permal Shankar, and Dr. Sudhakar Rao, my group here in IEEE and this thing. And I congratulate the TOCH Institute of Science and Technology for organizing this. It's a very, very meticulously organized. Here again, similar. Like if I'm not, if I'm allowed to repeat, the reason I'm here is Dr. S. Raghavan and Professor Permal Shankar. And it's my privilege to be associated with this STTP third phase. Hope we will see that. I hope the participants as well as organizers will be happy after after seeing the performance. Once again, I congratulate the organizers and thank the participants and other speakers with me. Special thanks to Professor Raghavan and Dr. Sudhakar Rao. Thank you very much.
Okay, thank you, sir. We have got Professor Mahadevan. He will tell one or two sentences. Then we have got a surprise guest from Jhansi. She's an expert in both biomedical and microwaves. And finally, she will conclude my talk with 2 minutes of her professional voice. Professor Mahadevan, followed by Dr. Shanas of Jhansi, the Dean.
Thank you, Professor Raghavan, for inviting me to speak a few words as a part of your guest speech. First of all, let me thank TOCH for having arranged such a elaborate weekly this in course STTP and packed so very well with different topics. And I'm happy that this time even we are topic on microwave filters are also included because that is a very important part of and plays a very crucial role in most of the spacecraft systems specifically, and of course, obviously in many of the other systems. So I'm happy that that is also included, and also the measurement part, which is generally neglected, is also included this time as one of the lecture course. So that is a very good thing. Others, of course, are part of the full antenna design and this of various systems. Okay, we will hear it when it goes. So I should really thank Professor Raghavan for having brought a lot of experts from various fields into this particular program. And obviously, the TOCH has been really very fast in organizing things. The previous one was hardly a week to 10 days back. Now the next one is already on. So I wish them all the very best. And I'm sure it will be very much appreciated by both students as well as the faculty who are all attending this. Thank you very much and wish you all the very, very best. Thank you.
And I request the Dean of Jhansi Autonomous College, Dr. Shahnaz Ayub,
Good morning, sir.
Yes, please. Your mic is working?
Yeah.
Yes.
Hello.
Yes, we are able to hear. Please. Hello.
Thank you very much, sir. Thank you very much.
Yes, please.
Yeah, am I called, sir? Am I called?
Yes.
Shahnaz here.
Yeah.
Shahnaz here, sir.
Yeah, 1 or 2 sentences we want from the dean.
Yeah, I am thankful and grateful for providing me this opportunity to talk with this intellectual galaxy, and it is my honor and pleasure to be part of this particular function, inaugural ceremony also, and part of this FDP also. And I am very much delighted that I am getting opportunity to have interacted with the great people, like the great personalities of this particular field. The father, we can call the father of this microstrip antenna in India, Professor Raghavan sir, Dr. Sudhakar Rao sir, and Professor Lakshmi Narayan and Merungu sir, and other speakers also, SS Patnaik. The schedule which I have gone through this particular STP, it's wonderful, and I think this 5 days program would definitely add values and knowledge to the participants' existing area of their work, and it will be beneficial to the researchers. And it is my pleasure that I am getting this opportunity to listen to the insightful speeches of great personalities like all this galaxy. Thank you so much, sir.
Thank you.
Okay, the principal, HOD, the last sentence I want to tell is, as far as Dr. Sudhakar Rao is concerned, he is unknown to Dr. Perumal Shankar. But Dr. Sudhakar Rao sent a black and white letter where he has mentioned, within 2 minutes of contact, I have come to know a unassuming, wonderful person, and he is no other than Dr. Perumal Shankar. So it is not Raghavan's words, it is the words of Dr. Sudhakar Rao, who is making India proud by staying in America. So I do not want to say much on Perumal Shankar, and he is the man behind of the whole 3-day FDPs. Definitely this should be brought out in any magazine, and I am sure that Dr. Perumal Shankar is able to do, because of the strong support of HOD, 22 faculty members, the principal, and the worshipful management. I thank everyone, and I'm sorry that I have taken some few more minutes extra when you are maintaining such a nice punctuality. Now, the final part, vote of thanks by the coordinator, Perumal Shankar.
Thank you very much, Raghavan sir, for your very kind words. Also, thank you, Sudhakar sir, Lakshmi Narayan sir, Mahadevan sir, and Shahnaz madam. Next, I call upon Dr. S. Perumal Shankar, coordinator of the STTP, for the vote of thanks.
Good morning to all. Being a grateful that can improve our attitude and even our experience, I take this opportunity to propose a vote of thanks to those who have contributed to this program. At the outset, I would like to take this opportunity to express my gratitude and thanks to AICT for having sponsored this 6 days virtual STTP. We feel blessed to have such a great humanist management, a group of extraordinary people who have been a constant source of inspiration to all of us. Their passion for knowledge and interest in learning from great minds guides us and guides us to look for a new avenues to conduct the program of this kind. They have been advocating the idea of attracting men of genius to our college to provide an environment for students to learn for them. We are very much thankful to our honorable founder, manager, and director, president, sir, secretary, treasurer, and our board of directors for their motivation. I express my deep and profound thanks to my most respected Dr. S. Raghavan, sir, chief guest of this inaugural function of this STTP for his help, support, mentoring, and constant patronage. Sir, you are the source of inspiration for me, sir, and for us also. Your nobility, generosity, and passion in guiding people and make them think and become great that attracted all people. It is a benign blessing and great honor for us. Your constant encouragement and support in the hour of need helped us to get all stalwart speaker in the STTP. Thanks to each and everyone. But considering the time limit, I thank all. Their lectures certainly flourish the research of youngsters in the field of antenna like previous two phases. The last two phases of this STTP were fantastic weeks, where learned gurus all over India reigned. We were quenched with ever-needed updated knowledge, pointing future scope and possible developments, and shared their experience, giving light even to technology nuances in the antenna area. It is fairly hard to get such lectures of these all remarkable, extraordinary, and world-renowned experts in one STTP. I thank all the experts in the first and second phases. And in this third phase, also we have remarkable, extraordinary, and world-renowned stalwart speakers. Thanking them with proper intonation would be much beyond my feelings. So yet, I express my sincere gratitude to all of them. My sincere gratitude and thanks to our beloved principal and our most respected HOD for their enthusiastic support. We recognize the value of everything we received, the invaluable contribution, and more importantly, the time and energy they spent with us. A special thanks to the organizing committee, that is the committee under Vinu Miss, as well as presently the committee is under Dr. Jnana Sheila Miss. Previously, it was under Dr. Vinu Miss, and all teaching and non-teaching staff for their unflinching support and coordination. Our heartfelt thanks to all participants from all over India for their active participation. With these warm words, I would like to conclude my vote of thanks. Thank you all.
Thank you, sir.
One small request to the organizers. I request organizers to postpone every lecture by 15 more minutes, because their lectures are very rare, and let them not stick on to the time. So let every time be shifted by another 15 more minutes or more than that. Thank you all.
Sir.
Sure, sir. Thank you, sir.
Thank you, sir. With this, we are winding up the formal inaugural session. We surely hope that with this STTP, academicians and engineering professionals can gain exposure to the latest trends in antenna and design from core to the fine edge of application. So we'll be starting our first session. So it gives me great pleasure to extend to you a very warm welcome on the first session of phase 3 of the AICT sponsored 6 days short-term training program on the topic Trends and Technologies in Antenna Design and its Research Scopes. Today's session is on the topic Antenna Fundamentals, Design and Hardware Development for Space, Air and Ground Communications, and is handled by Dr. Sudhakar Rao. Dr. Sudhakar Rao is currently working as the Senior Technical Fellow at Northrop Grumman Space Systems, providing technical leadership for all divisions of Northrop Grumman in the areas of antennas and payload development for various key programs, proposals, and IRAD. Dr. Rao received BTech from NIT Warangal in 1974, MTech from IIT Kharagpur in 1976, and PhD in Electrical Engineering from Indian Institute of Technology Madras in 1980. He worked at ECIL Hyderabad and also at LRDE Bangalore, and was a postdoctoral fellow at the University of Trondheim, Norway, following which he was a research associate at the University of Manitoba, Canada during 1980s. Over the past 37 years, he worked at Spar Aerospace Limited Canada, Boeing Satellite Systems, Lockheed Martin, and now at Northrop Grumman, and contributed to antenna and payloads for more than 85 different satellites. His work on development of radiation templates for complex satellite antenna patterns for interference analysis was adopted and recommended by the International Telecommunication Union in 1992 as the worldwide standard for satellite manufacturers and operators. He authored over 210 technical papers and was awarded with 56 US and European patents and 5 trade secrets. He received several awards and recognitions that include IEEE Benjamin Franklin Key Award in 2006, Delaware Valley Engineer of the Year 2008, and Asian American Engineer of the Year 2008, IEEE Judith Resnick Technical Field Award in 2009 for pioneering work in aerospace engineering, Boeing's Special Invention Awards, Martin's President Award 2009, Professional Excellence Award from the Council of Indian Organization, and the 2017 and 2020 Northrop Grumman's President Award for Innovations and Contributions to the key programs, to name a few. He received Distinguished Alumni Professional Achievement Award from his alma mater, NIT Warangal, in 2016, and IET's Professor S.N. Mitra Memorial Award in 2016. Recently, he received the 2020 IET's Biman Behari Sen Memorial Award. Currently, he is appointed by the IEEE Board of Directors to serve as the IEEE Fellow Committee member for 2020 and 2021. I hand over the session to Dr. Sudhakar Rao.
Thank you, madam, for the nice introduction. Can you hear me?
Yes, sir. Thank you and welcome, sir.
Okay. Thanks for the organization of TOCH for inviting me, and especially thanks to Professor Raghavan and Professor Perumal Shankar. And hope all attendees will enjoy this 6-day STTP festival and learn something. And at the same time, even the speakers, I would say that try to be in the session. So you can always learn from others. So I think learning is a continuous process. So I will attend as much as I can till I think midnight, but after that I have to sleep. So so anyway, my talk today is antenna fundamentals, design and hardware development for space, air and ground communications. So what I want to say is how you take the fundamentals into the design, and at the end, unless you do the hardware development, for any industry you're working, there's no point. I think it doesn't matter. You could be a great scientist, but if you cannot develop the hardware, it's not good for the company. So always I would say that engineers have to work like engineers, not like scientists. Doesn't matter how many papers you have. At the end, I think what you do for your company is more important. If you're working in space, of course, you have to develop the space hardware. If you're working in the aircraft industry, you have to develop payloads or hardware for aircrafts. If you're working on the ground side, you have to develop relevant hardware suitable for the ground side, ground communications. So this is my agenda. I think I want to start with the role of antennas in communication, then go with antenna fundamentals. I'll briefly tell about the fundamentals, but I saw other lectures. I think they'll be dealing with some of these fundamentals as well. So then I give an introduction to satellite antennas. So some of you might have seen these, but I'll try to keep them brief. But this is for new people, so I thought I'll keep them. Then I will discuss about reflector antenna basics, because that's the mostly used hardware for either satellites or the ground stations or even aircrafts. Then I'll talk about phased array antenna basics. So all these antennas, either reflector antennas or phased arrays, people think it's very difficult to design. But if you understand the basics, it's very easy to design, I would say. Probably you can complete the design in a day or two, given the requirements. It shouldn't take long. You don't need to do tedious simulations and you cannot design any systems by simulations. You use simulations to prove the design. So initially, you have a good starting point. So that's where I think I would say all the engineers to focus on, not just EM simulations and try to get some results compared with measurements. That's not the way to do. At least for industry. For universities, it's fine. So I'll talk about some recent developments I've been doing for the past 5 to 6 months this year on ground and vehicular antennas. So these are some interesting things there. So I'll want to talk about those. Then there is satellite hardware and test. Testing is very important. So I think there's a special session on that. So I won't describe too much, but I'll keep a couple of charts on how to test and what are the test facilities you need to validate this hardware before you install them into any hardware. Then some conclusions I'll leave with. So basically antennas are eyes and ears of any communication system. Doesn't matter what you have on the satellite here, what you see. So for the satellite, I think, of course, what you see here is a deployed view. You can see only solar panels deployed. This is the top right picture. And then antennas which are deployed. So you cannot, and the spacecraft body. So here, I think the key issues are thermal because satellites go through very extreme temperatures. When the sun is hitting on them, they go almost 170 degrees, 180 degrees C. And when the sun is behind, so it's a cold for the satellite, so it goes to minus 170 degrees. So total, there is a temperature excursion of 350 degrees. So when you design these components, you don't design at ambient temperatures. So you have to take the thermal guard bands, temperature effects into account, and design all these components, especially the filters are sensitive to the passband moves around over the frequency. So you need to design over wider frequency bands. So next one on the bottom left is UAV, unmanned air vehicle. So here the things are, antennas have to be very compact, very lightweight because of the UAV, you cannot have heavy antennas. And most of the antennas, you have to have 4 pi steradian coverage, either 2 pi or with the 2 antennas or complete 4 pi steradians. And if you go to the ground antennas, it's totally different because they have to withstand the high winds. So when you design these, it's, I would say 60% is mechanical, probably about 30-40% is RF. So you have to make sure that it withstands the wind speed, sometimes maybe 130, 140 kilometers per hour. So you need to withstand dust, sometimes sand. So all these things you need to be aware of. So what is the role of antennas in the day-to-day communications? I think the role is very significant. As you can see on the top left, there is a satellite, advanced EHF satellite, which I'll talk about later. On the right side, E3 airborne warning and control system, AVAX. You can see the large phased array on the top of the aircraft. On the bottom left is the B-2 bomber, which Northrop Grumman, my company, is making. Right now, we are making a contract with the next generation advanced B-21 bomber. We just started that about a year back, and development phase it's going on. So that's a program for the next 20-30 years. On the middle, you can see Arecibo, Puerto Rico. That used to be the largest telescope in the world, about 1,000-foot diameter. But I think the Chinese have made 1,500 feet diameter telescope last year, a radio astronomy telescope. But now JPL is making, planning to make a telescope probably even 2 times larger than the Chinese telescope, almost 3,300 feet. So they're planning now, I think. So probably I'll be consulting on that one as well. So for a few years. And on the right side, you have the DSN network, Australia Deep Space Network. So there are 3 deep space networks, one in Australia, one in Africa, one in California, USA. So 3 of them, they can track any satellite and they can give the information for the operators. So this is a 64-meter DSN antenna. So this is the geostationary orbit on the bottom left. So this is the geostationary belt in the equatorial plane where you have all the satellite parked with the 2-degree spacing. So this is in 2001, about 1,700 satellites, now almost about 4,000 satellites. And in the next 4 years, 5 years, I think it will be going to be almost 10,000 satellites. So there has been exponential growth in the satellites, and sometimes you have to, same orbital slot, you can see multiple satellites parked in at a higher altitude. So in case if one fails, actually you can bring that down without delaying the services, communication services. So currently there are 2-degree spacing in the orbital arc, all the adjacent satellites. The main reason for that is the ground stations, with even the largest ground station, it can distinguish only satellites 2-degree apart, so that you won't get with sufficient isolation between them. But to accommodate more satellites, you need to reduce the spacing to about 1 degree or even half a degree in future. So we are working on that. So basic thing is you have to go into more higher frequency bands. Right now we are working on instead of C and KU bands, which are conventional, we're working at V and W bands, which are transmit is 71 to 76 gigahertz, the receive is 81 to 86 gigahertz. So it gives a very large spectrum. At the same time, it allows the ground station to identify or differentiate satellites which are much closer than 2 degrees, 1 degree or half a degree. And then there are other satellites, Asian cellular satellites, which I worked at Lockheed Martin, and EchoStar 10. This is a direct broadcast satellite launched by, a few of them are launched by Lockheed Martin. So what is a satellite? So satellite is a relay in space. So its main objective is to connect users on the ground, user to user or user to ground antenna, or several ground antennas, etc. So basic function is to connect users on the ground. So why we use it satellites instead of microwave relays? Because they're much cheaper, 10 to 20 times cheaper than microwave relays, where you have to have repeaters every 30, 40 kilometers, and real estate is large, and then you have foliage effects due to forests and mountains. I think sometimes you won't get the signals. So a lot of problems, but in the satellite, I think if you have geostationary satellite, which is at 36,000 kilometers, 1 degree corresponds about 630 kilometers on the ground. So the angles are very small, plus minus 8.7 degrees. So that means since angles are small, most of the countries are even much smaller than 8.7. So typically 2 or 3 degrees, etc. So you can get very high gain. And at the same time, you won't have any problems with foliage effects and any blockage due to mountains, etc. It covers the whole thing. So of course, one satellite covers only 1/3 of the Earth. So if you have a satellite in the Asian Pacific region, it covers the Asia Pacific region. You need one in the European region and one in the North America to cover the North American satellites. So basically 3 satellites, I think it will cover the complete globe. Typically 4 are used with some overlap and some redundancy. So any constellation, typically about 4 satellites are needed if you're in the geostationary orbit. But the key considerations we have is thermal. As I said, it's very difficult. Thermal excursions are very large, almost 350 degrees C. Other is, I think once you launch the satellite, they is sort of probably $500 million or something. So you want to pack in as many channels as possible. At C-band, probably 32 channels, sometimes even more. So all these channels actually have high transmit power. So actually high power is going through some of the antenna components. So when you design these components, you have to make sure that power handling is, you meet the power handling capability with the margin. Typically by design, we use a 6 dB margin. So they can go up to 2 kilowatts, sometimes even more. So if it is a 2 kilowatt power, then we design everything with the 6 dB margin, which is 4 times 8 kilowatts. So if you don't meet that for some reason, you have to test it. But when you test it, you test it with the 3 dB margin. So that means 4 kilowatts. So testing is very expensive. So we go through several design exercises and even manufacturing the choice of materials to make sure that the antenna handles high power. PIM, passive window modulation, I'll talk about it later. So that's also another phenomena. You have to make sure that you don't have any passive window modulations, especially when you have multiple transmit channels beating against each other. All these intermods go into sensitive receive channels. So if they saturate the receivers, then the receivers won't work and the satellite won't work. So you have to be careful. Typically, they are minus 135 dBm or minus 140 dBm, depending on the frequency. ESD, electrostatic discharge, that's very important since it's vacuum and high power is passing through. You want to make sure that no charges are built in into the payload or antenna systems. So what you have to do is you have to use pristine materials so that like if you use a dielectric, of course, they collect the charges. So over time, actually, if you don't bleed through the spacecraft body, over time it will blow up and then whole payload is gone. So rule of thumb is no dielectrics in space. So that's the reason you don't see. Can you mute your mics, please? So ESD is a key issue, so that's the reason why we don't use dielectrics in space. I think some dielectric lenses people have used in the past, especially US defense, but it blew up and people even now try to use, but my rule of thumb is no dielectrics in space, even as supports or even to hold even the pin, some support structures, you don't want to use that. So why end up into problems? So cross-pole is very important. So we talk about 33 dB cross-pole discrimination. So that means any part, say if it is an Indian satellite covering India, so any point in India, co-pole to cross-pole ratio has to be more than 33 dB. So that's very, very stringent. So if you have to make that spec, you have to at least meet 38 dB or so, at least about 5-6 dB margin. So by analysis, you have to show that. The reason for that is sometimes you want to use dual polarizations. So if it is linear, you want to use both vertical and horizontal. So that means if you want to do both polarizations, then you can increase the satellite capacity by 2 times. So, but on the other hand, you want to minimize the interference between them. So you want to have low cross-pole isolation. And bandwidth is very important. Sometimes we talk about 60-70% bandwidth. So all these reflectors or other feed systems you use, I think they have to carry that bandwidth. So you make sure that you design over wide bandwidths because they have to cover both the transmit receive. So like C-band 4 and 6 gigahertz, Ku band, and Ka band 20 and 30 gigahertz. So signal to noise ratio is what is figure of merit of the satellite. So you can see there, I won't go through all the details, but you can see. So a lot of negative numbers. I think you have SL is the space loss. I think I can't see it here at the bottom. Okay. So ERP is nothing but a gain of the transmit antenna plus power per channel. So this is all in dB, so you can add them up. GOT is the sensitivity of the or quality of the receiver. Gain to system noise temperature, which is the gain of the receive antenna minus system noise temperature. 228.6 is Boltzmann constant, which basically relates the energy to temperature at particle level. So that's typically joules per Kelvin or dBW per Kelvin per hertz. And SL is a big negative number. So it's space loss, both forward link and return link. So it's where 4 pi r over lambda square, so 10 log of that. So if you take that, it comes almost like 300, 400 dB loss. 10 log BW is the bandwidth in hertz. So that's also a negative number. So a lot of negative numbers, so a lot of pressure on, of course, you can't increase the PI that much because then your core handling is limited and spacecraft becomes complicated. You need to dissipate the heat. System noise temperature is standard, so you cannot optimize. Of course, there is a LNA noise figure you can reduce a bit, but that's still, I think it's a negative number. You can't do too much about it. So a lot of pressure on antenna engineers to improve the gain of the transmit and receive antennas. So here what you see in the middle is a typical communication satellite. where you have satellites in the geostationary orbit. Sometimes if it is constellation of satellites, they have to talk to each other. So that's an inter-satellite relay that's done at V-band. Then you have from the ground antenna, say if it is a C-band system, ground antenna transmits at 6 gigahertz, and the satellite receives at 6, down converts to 4 and transmits back to the ground, and the ground receives at 4 gigahertz. So the one where satellite receives at 6 is a uplink, and when the satellite transmits 4 gigahertz, it's a downlink. And you have another link which is called TTNC, telemetry and telecommand system. That's also very important. So that's done through omni-type antennas, biconical antennas, or sometimes even horns. So that link is also very important, because if that link fails, that's the only link available in the transfer orbit. That link fails, the whole satellite is gone. So antenna design is very critical to satellite payloads. So these are some designated satellite service by International Telecommunication Union. The ones we are interested in is in broadcast satellite service, BSS. So this is where you receive all high definition TV channels on your rooftop 24-inch pizza-sized dish. Fixed satellite service, this is mainly operated by the nations like India, to cover the India. US has a CONUS coverage, so there are a lot of operators doing that. Inter-satellite link we talked about, and that's at V-band for a constellation of satellites. Mobile satellite service is typically done at L and S band. So these needs a very different technology for antennas, largely deployable mesh type reflectors. And personal communication service, PCS, is coming fast. So that's mainly high data throughput satellites. Currently, they have, we're building one beyond 1 terabits per second capacity. Typical is 10 gigabits per second capacity. So to get that increased capacity, you have to go with multiple beams. So we'll talk about that later. So here, I think all the three components of the satellite I've shown. One is a satellite, of course. Other is a ground antenna, we talked a bit. Another is a launch vehicle. So typically launch is done in 3 stages. So first stage takes the spacecraft to about 50 miles above the Earth. And then the second stage takes it about 100 miles above the Earth and puts in the transfer orbit. So once you're in the transfer orbit, then apogee kick motor takes the spacecraft to any altitude you want, either medium Earth orbit or geostationary orbit or low Earth orbit. So all 3 components are important. If anything fails, you don't have a communication link. So here I'll show you some video. You can see maybe a couple of minutes.
DHF payload, heart of a system delivering unprecedented levels of assured networked interconnectivity to rapidly deployable maritime, air, and ground forces, flexibly, where and when needed, immune from denial of service attacks, available in all levels of conflict. The payload puts the advanced in advanced DHF. A highly advanced digital processor serves as a switchboard in the sky, providing an order of magnitude increase in capacity versus Milstar, while supporting thousands of direct and rapidly reconfigurable flexible network connections between users on a variety of operational platforms. The processor implements advanced security and anti-jam waveform features to maintain both confidentiality and undeniable availability of U.S., international partner, and coalition networks operating at multiple security levels and within separate security domains. As with Milstar, the advanced DHF payload supports user logon and communications at lower data rates, worldwide, anytime, without prior coordination, and in the most hostile environments imaginable. And like Milstar, the payload features highly sensitive receive equipment, capable of accurately processing lower power spread spectrum signals in the EHF band, enabling low probability of detection, stealthy communications in support of special operations. The payload's fast-hopping uplink and downlink phased array antennas can flexibly cover a much wider area of the globe simultaneously with high-capacity service. While both Milstar 2 and Advanced EHF provides 6 1-degree spot beams, which can be steered to anywhere in the satellite field of view via gimbal drive antennas. The advanced EHF phased arrays support an additional 6 1-degree shareable spot beams, instantaneously steerable to any location within the satellite field of view. Operational planners have the option of allocating the capacity associated with each shareable beam among up to 4 separate regions within the satellite field of view, done on a hop-by-hop basis in milliseconds, transparent to individual users. Even with each payload's ability to deliver high-capacity coverage to upwards of 30 separate regions, there still could be a need to provide higher capacity service to isolated users outside of these regions.
Okay, this is
The advanced.
So we built 6 advanced EHF satellites, Northrop Grumman. So 6th one was launched last year. So all 6 are working beautifully and giving, they have been used in many war situations in Middle East and other places. So they're the main source for our military to provide communications for soldiers on the ground. So I think we are actually making, we have another contract to build next generation advanced EHF. So that will be starting probably in the next couple of months or so. So anyway, different satellite antenna types, high gain antennas, typically 30 dBi to 70 dBi. So they're typically reflector antennas are used. Probably I would say about 90% are reflector antennas. Lens antennas almost zero, hardly used because of the ESD issues I talked about before. Dielectric lenses, you can do waveguide lenses, but the mass becomes so large, then you have to zone the lens. When you zone the lens, it becomes narrowband and it has other problems. So it's not a good design. Array antennas are occasionally used, like you have seen on advanced EHF, where you need beam flexibility, very fast switching of the beams. So you have to use phased arrays, but that's mainly for military applications. Communications people are trying to do, but they're expensive and also they consume a lot of power. DC power, dissipating the big power is through heat pipes is a headache. So I think still I think it's in the development now. But I would say that reflector antennas are widely used. Medium gain antennas, we use them, global coverage horns for the global coverage for in-orbit testing, etc. They're in the range 15 dBi to 25 dBi, and they cover global probably plus minus 9 degrees at the most. Low gain antennas, they're used for TT&C when the vehicle is in the transfer orbit, and also they can work on once it's in on station as well. They're biconical antennas typically. Sometimes waveguides are used to reduce the cost. Sometimes horn antennas are used. So different services we talked about, fixed satellite service, broadcast satellite service, mobile satellite service at low frequencies, inter-satellite link, inter-satellite service ISS we talked about at V-band for constellation of satellites, PCS personal communication service at 20 and 30 gigahertz. So that is for high data throughput for high data throughput satellites. So all these you can see different types of, on the top right you can see how the spacecraft body when it's deployed looks like, all these reflectors, several of them, 6 of them, sometimes sub-reflectors, 2 on the native panel and associated feed horns. Typically, before I think we used to use feed arrays, now we don't use that. We typically use a single feed for transmit receive to reduce the cost and also one antenna can do both the TX or X. So otherwise you need 2 antennas. Lens antennas, you can see the zoned lens on the middle. So surface you have to zone it to reduce the mass. But ESD is a big issue. I think you can do on the surface by some coatings, metallic coating to minimize the ESD, but the bulk charges I think developed in between, I think very difficult to discharge them through any metallic ground plane or spacecraft body. So that's why it becomes almost useless in space. The horns, I think we are also working on multi-mode horns. I think people use corrugated horns quite a bit, but corrugated horns are very heavy and they have problems. If your manufacturing is not perfect, then you get some internal resonances over narrowband resonances. So that will limit your power handling capability. So right now, I think technology use smooth wall horns, multi-mode horns. I can explain that later. So they're lightweight and they can carry multiple frequency bands as good as a corrugated horn. Okay. So all these antennas you can design like you see on the top right, say 6 different reflector antennas, but when you put them together on the spacecraft body, they don't work properly because of the coupling effect scattering from the spacecraft body, which is metallic. So I think you can design them independently, but only you can finalize the design after you do the spacecraft scattering analysis. So once I think you finalize that, you finalize the where to put these antennas, what is the separation you need, etc. And then taking into account, you have to give field of view for each of these satellites so that they don't interfere with each other. So once you do that, I think that takes about 1 to 2 months. So after that, I think your design is frozen, and then you go and manufacture the antennas and payload. So some basic fundamentals about EM wave propagation. We all know electromagnetic wave is nothing but a disturbance which travels at speed of light. It has certain wavelength, and it's characterized by oscillations of electric and magnetic fields. You need both electric and magnetic fields for the wave to propagate. So different types of propagation. We have direct wave propagation, line of sight, which is used over narrow distances like microwave towers, cellular phone towers, etc. Ground waves, they can go slightly more larger distance. They're used over the horizon applications. Mainly government radars work in that frequency range. And then you also have sky waves, which basically reflect from the ionosphere. And then that way you can you can communicate over over a larger distance. So you basically use the ionosphere to reflect the electromagnetic waves, so that you can do at certain frequencies. And above 30 megahertz, I think you use space waves because they are not attenuated by the minimally affected by the ionosphere, so they don't reflect back, they propagate. So all the space satellites use the space waves. So how antenna radiates? So antenna radiates due to time varying currents, which are coming through varying charge accumulation. You can see on the right side a dipole, how the charges are developed at both ends, positive, negative charges. So that creates a distribution over the dipole. You can see cosine distribution type. And then radiation will be figure of 8 type radiation. Typical dipole, you can see the current flow in the red, and then E fields both in the forward hemisphere and the backward hemisphere. So figure of 8. So how they radiate? I think they radiate to radiate these electromagnetic fields. You need an antenna. So what is an antenna? Antenna is a transmission line, and then it needs a tapered transition. So tapered transition is nothing but the antenna. So what it does is basically it matches the transmission line impedance to free space impedance, and secondly, it dictates how the antenna pattern has to be, whether it's narrowband or wideband. And what gain you need. So based on that, you design this tapered transition, which is antenna. So controlling the antenna radiation is very important. So that's what most of us spend on, how to design the antenna system, which matches to the transmission line, and at the same time, it gives the right radiation in the far field. And some definitions about polarization. So here you can see vertical polarization, horizontal polarization. So that is basically defines the direction of the electric wave vector. So if it is vertical, then it's vertical polarization. If it is horizontal, it's horizontal polarization. But for the satellites, the definition is a bit different. So if the polarization is, see the top right-hand picture of the CONUS, continental United States. So if the electric vector is parallel to east-west, it's horizontal polarization. If the electric vector is parallel to north-south, it is vertical polarization. So that's the only definition we use. So it varies from country to country, depending on the coverage. And then the circular polarization, to do that, you need the two equal vertical and horizontal polarizations, equal amplitude, and you need them in phase quadrature so that your electric field vector rotates as it propagates. And if it rotates clockwise, it's called right-hand circular polarization. It rotates anti-clockwise, it's called left-hand circular polarization. It's very important to know the sense of polarization, because sometimes if you design like 2 or 3 satellites are designed with wrong polarization, and the ground cannot accept, because grounds are designed with to receive only that polarization, so they have to modify the ground stations or a lot of additional work and cost. So how antenna radiates? Of course, isotropic radiator. So this is only for theory. So there's nothing exists like isotropic radiator. So you cannot make an isotropic radiator. So we use that. If it radiates uniformly in 4 pi steradians, it's called isotropic radiator. And we use that as a reference to define any directive antennas. So directive antennas, that's what we need, because we need certain gain. So if your beam width is narrow, you can focus all energy into that very small region, so you get very high gain. So we refer always directivity of the antenna to dBi. Same thing, gain of the antenna too. So sometimes engineers get confused, directivity and gain. So directivity is what you compute. If you're using TICRA or any other code, reflector code, what you compute is the directivity, that is relative to the aperture. So gain is you have to account for all the losses, feed losses, reflector losses, waveguide losses, etc. So they're significant. I think for satellites, it's almost like maybe 1.1 to 1.5 dB loss. So you need to account them properly. Then only what we are interested is in gain, not the directivity. So that means you have to increase the directivity and you have to reduce the front-end losses. So you can see the omni patterns, how it looks like, and the directive pattern, you have half a beam width and then side lobe sometimes. So you need to reduce the side lobe, some applications, especially for satellites, so for radars also sometimes, but effective isotropic power, radiated power, we call it EARP. So that's nothing but input transmit power times gain of the transmit antenna. So it has to take into account the losses in between. You have high power amplifier giving you the power what you need, and then you have some losses in between. You have cables, filters, waveguides, some OMTs, feed horns, reflectors, etc. These are all losses. And then you have the directivity coming from the transmit antenna. So that's figure of merit of the downlink antenna. And GOT is the figure of merit of the receive antenna. So G is the antenna gain, and T is the system noise temperature. So system noise temperature you calculate based on the antenna noise temperature. So if you're looking, satellite looking at the ground, whatever you're covering over the ground, plus minus 8.7. So it's 290 degrees. And then you take the radiation pattern and weigh them. Beyond that, I think it's a cold sky, so 5 degree Kelvin. So you weigh them according to the radiation patterns and then calculate the antenna noise temperature. Typically, it's less than 290 degree K, depending on where your coverage is. It's sometimes even 250 or even 220 degree K. So you have to figure out the losses in between the LNA and the antenna, and then noise figure of the antenna, and some back-end losses also you have to account for when you characterize the system noise temperature. So all these things are important, but the key thing here is the transmit. Nowadays, I think all the transmitters, we know how much power they can handle at C-band, Ku-band, they're standard. LNAs, we know what is the noise figure, it's all standard. So only variability you get is antenna and the losses in between. So a lot of work is going on to reduce the losses of antenna components, and at the same time coming up with high efficiency antennas as well. So this is another chart to show these are the antenna gain pattern. If you translate, you can see the 32 dBi, 30, 28, etc. If you translate that to ERP patterns, you add the power, of course. So you can see how it looks like on the top right. And then on the bottom right, you can see how the G over T looks like. Because G over T is 290 degrees Kelvin is minus 26.2 dBK, I believe. So you add that to noise figure of the LNA, etc. It's sometimes almost 30 dB negative. So you can see all the G over T contours. So this is for contoured beam antennas. For spot beams, it's G over T is as high as 20 dB per K for especially high throughput satellites. So some, I think, you have to know the theory, radiation from the apertures. So we all learned from our college how a square aperture, what is the pattern it looks like, sin x over x. X is kd sine theta. D is the size of the aperture. K is the wave number. So it's you can see the patterns. It has side lobe levels of about 13.2 dB relative to the beam peak. So circular aperture is 2 J1x over x. J1 is the Bessel function of the first kind, and x is Ka sine theta. Again, A is the radius and K is the wave number. You can see the pattern. Of course, it has lower side lobes, about 17.8 dB relative to the peak. So these things are only theoretical, but when you do the practical feed or any aperture, it looks something like this. This is the radiation from corrugated horns. You can see the cross pole is very low, almost 40 dB. And this pattern either looks like a circular aperture or square aperture. So it doesn't have any side lobes because that's what we want. Anything you have side lobes, so they're not captured by the reflector. It contributes as a spillover energy, so that's power lost. So we don't want that. So we design with very low side lobes or no side lobes. Reflector antenna basics, I think it consists of two major assemblies. Of course, the reflector assembly and then the feed assembly. So reflector assembly, of course, the size provides a gain. So since you can increase the size of the reflector, you can get the gain very cheap. Unlike phased arrays, which are expensive, you need thousands of elements to get very high gain. So that's very expensive. It determines the coverage shape. So it determines the scan loss. So if you have multi-beam system, beam squint. So it has a reflector. So sometimes you have to have a thermal paint or cover on top of it to make sure that you protect it from the temperature excursions. I have deployment boom, mechanical assemblies. Sometimes you need to gimbal that. So what is important here is how well you can make the reflector. So surface accuracy is very important. So typically we use lambda by 100, sometimes even more. So sometimes your RMS cannot be more than 5 mil or so. So that's very, RMS error has to be very small. And the reflection losses have to be small, and cross pole has to be very high. Almost it shouldn't give any cross pole, and it has to be thermally stable. So feed assembly is very important actually, because feed assembly is not just the horn. So it's OMT, polarizer, filters, diplexers. Test couplers are used for spacecraft level testing when the satellite is on the ground. So you inject the signal and make sure that you're getting the right power through amplifiers or right noise figure through LNA. Then you need waveguide interfaces to connect to the repeaters. So function of that is provide proper illumination on the reflector. So we use typically 15 dB illumination on the reflector. Sometimes people use 10 or 12 dB, but that's not a good thing. So minimum, typically these feeds are dual band, works on both the transmit receive bands to reduce the cost of the reflector. So one reflector instead of two reflectors. So when you do that, I think you have to make sure you get at least 15 dB illumination on the reflector. So it also dictates the bandwidth. Sometimes you need very high bandwidth. Maybe you need to support multiple frequency bands, maybe 3, sometimes 4, 5. So we can do that. So basically horns and horn components are very important. Polarization, it defines the polarization, whether linear or circular. Cross-pole isolation is important. So if you have offset reflector, the reflector doesn't depolarize. It's only whatever feed depolarization is the cross-pole isolation. So you have to design these feed systems with extremely low cross-polarization levels, almost 40 dB level. Filtering is important, so that's also part of the feed assembly. I call it feed assembly because you cannot design these components independently and put it together and make it work. So you have to, current day technologies, which we started actually at Boeing, and you don't design these components individually, you combine them. You design, of course, initially individually, but you put them together and you need to analyze the whole feed assembly, including everything up to the waveguide interface. Then only I think, once you do that, I think, sometimes higher order modes are generated in between. So you have to know how to suppress them. So when you do that, I think you don't need even to measure nowadays. I think if you do proper analysis. So insertion loss is important, power handling is important, temperatures are important. You need to design especially filters to cover the wide, put a thermal guard bands both on the low end and high end of the pass band, and design over wide band, low PIM and wide band. These are some reflector types. Might have seen, heard about it. Parabolic reflector, focal fed. So feed is at the focal point and reflector is parabola. So F over D, certainly it has certain F over D. Then you have offset reflector. So we don't normally use center fed reflectors, most applications, because there's a blockage.
ऑनलाइन पेपर थे सबके, मैं जो उधर भेजते रहते हैं और हो गया. अच्छा.
Can you mute, please? I think I'm hearing crosstalk. Can the organizers mute the listeners?
Okay, sir. Okay. यूनिवर्सिटी का था पेपर, एमएससी मैथ था. अच्छा. मैथ में तो थोड़ा फिजिक्स भी, हम फिजिक्स में मैथ पढ़ते ही हैं, तो वही आए ये लगभग. अच्छा.
So the dual reflector systems, I think offset reflectors we use because it avoids the blockage. So you don't lose any power due to the blocked portion of the feed or any other sub-reflectors, etc. Then you have a Cassegrain system where you have a sub-reflector. So feed is very close to the vertex of the main reflector, which is parabola. So then you have a hyperbola sub-reflector. Then you have two foci. One focal of the main reflector, other focal is focus of the feed, which is hyperbola has two foci, parabola has one focal point. Gregorian instead of this is also very widely used. Instead of hyperbola, you have ellipsoid. So you have a similar thing, except it has some advantages compared to. So all these systems are very important, and the gain of these antenna, or directivity in this case, we refer to 4 pi over lambda square, for pi d over lambda whole square times epsilon. So I think this equation is wrong. So epsilon or eta is the efficiency. So it has several parts here. So you have to make sure that you maximize your efficiency. So typically you can get about 80 to 85% efficiency. Anything you get less is not good. So you have to check your designs. Some equations here, I don't go through all these equations. Again, this is offset parabola. So when your feed is at the focal point, it is focal plane. Most applications use this. Some applications you have to defocus. You have to use array of feeds for some other applications. So when you do defocus from the focal plane, use it's called image plane. So you need more elements contribute to the beam, and you can shape the beam as well as needed. But the equations won't change. I think you can refer to this book, my book published by Artec House in 2013. All the equations are given. So basic thing here is the eta f. So once you calculate the eta f, you can get the directivity. You can get the scan factor when you defocus a feed from the focal plane. How much scan loss you get, you can always calculate very easily. And this is how the efficiency looks like on the left-hand side. If you use something like 1 lambda type horn, you get only 48% efficiency. but we don't want to do that. So we want to maximize. So this is for the single offset reflector. You can get about 80% close to. If it is a dual reflector, you can get at least 83, 84% efficiency. So nothing, 85 probably is the limit. I think anything you get beyond that, you have to question. So it's not practical. And as you increase the horn size, of course, your taper goes increases on the reflector, or side lobe reduces, etc. So we can look into all these things very easily. And then this is what size of the reflector relative to wavelength on the x-axis. On the y-axis, you have directivity on one side, the dBi, and the 3 dB beam width on the other side. So the biggest reflector, 200 lambda here, has a gain of almost like gain of 55 dBi, and then the beam width is very narrow beam width, probably 0.4 degree or so. But as you go down, I think your directivity reduces and beam width increases. So now some basics about phased arrays. So like I said, phased arrays are not very difficult to design. It's actually very easy to design. And you can probably do, if you have a calculator, you don't need even to log into the computer or sophisticated MATLAB and other things. You can just do on a calculator or even manually. There are two types of designs, array lattices you have. One is the square grid. You can see on the left side how the elements are placed. So there's a certain spacing ds. And then the other is the hexagonal lattice. People sometimes call wrongly as triangular lattice because it's not. Unit cell is always hexagon. So it's a hexagonal lattice. So these are the main lattices, but people try to do other things like sparsed arrays and thinned arrays, etc. But there are practical problems with that. I mean, theoretically you can do that, but when it comes to practice, you cannot, because all amplifiers, it has to be evenly spaced. Otherwise, if you keep on varying, it becomes very complicated, especially for the heat pipes where you want to dissipate the heat. And it varies from satellite to satellite, so you don't want to do that. So regular spacing is always good. So simple and works best. And also other arrays have problems too. So what are the key requirements? We can see the phased array. You have number of elements. You have some filters, of course, depending on the band, you have to reject some frequencies. You have LNAs. This is the receive side I'm showing. So each element has an LNA. And then you have 1 to m dividing network. So basically you need m number of beams. So you have to divide signal of each element into m waves. And then pass them through variable attenuators and variable phase shifters. And then m to 1 combiners, you combine all the signals from the n to 1 combiner, all the n elements. So that becomes a beam. So you have a number of beams, m different beams, so you can create. So these combining dividing networks are could be done at RF, could be done at IF, or nowadays we are doing it digitally because it's very easy. So what are key requirements? The gain or directivity, scan coverage. Sometimes you have to scan these arrays. So the coverage is very important. How far you want to scan the beam. Beam width is important. Polarization. Sometimes you may not have enough space to put dual polarization. So you have to look into that. If it is CP, you have to put a polarizer in between element and the filter. So that's part of the element. Side lobe level, sometimes you have to taper the distribution to lower the side lobes. Sometimes uniform distribution is fine. ERP and GOT that derive the requirements. So what are the design parameters? You choose the array lattice first. I'll explain how to choose what are the trades later. Element spacing. So if it is a square array, then you can see the equation. So maximum spacing you can put, always you design when you choose the element spacing, you design over the highest frequency, lambda at the highest frequency of the band. 1 over sine theta m is scan angle, maximum scan angle, 30 degrees or 60 degrees or even 80 degrees, 70 degrees. So the second parameter on the denominator is sine theta g. Typically, people use 1 for that because that's where most of the textbooks, radar textbooks have, like Bob Malo's book, if you see, that's a famous array antenna book. It always shows 1 because he's designing for radars, but that's not general enough. So you have to have sine theta g. So theta g is the grading lobe location. So of course you don't want the grading lobes in the coverage, but you don't need to keep the grading lobes at 90 degrees. So you have to keep them at slightly beyond the scan range. If it is 30 degrees, probably 35, 36 degrees. So that so what it makes is your spacing, I think it increases slightly compared to theta g at 90. So that means your element directivity increases and number of elements you need is much less. So number of elements dictate the cost, so you can reduce the cost. So you want the grading lobes, but you want them outside the coverage region. Same thing for a hexagonal. Hexagonal also gives you additional increase in the spacing by about 15% because of the nature of the cells. You can derive pretty easily the equation. So based on this, I think you select the element size or spacing. And once you know the spacing, element, you know the efficiency, and then you know the element gain or directivity, and then you can calculate the number of elements you need for the array. It's very easy. And these are the equations. I think it's in my book. I think I forgot the reference here, but I might have it later. So this is published in the April Antennas and Propagation magazine. It's a design of basically it talks about design equations for how you design the reflectors and phase array. So it's it came in the April issue of Antennas and Propagation 2020, so you can refer to that. So these are the parameters, I think here. I don't want to go through that again. So scan loss, you can determine very easily from the equations. So all these you have to go with some margin as well, implementation margin, typically 0.5 dB to 1 dB, depending on the complexity. So unless you have implementation margin, you cannot design these phased arrays. They're complex, so you need to include that. And then you can determine the number of elements what you need. So this is the paper I think I wrote with Colin Ostrod is a student from, he came for summer training with us, and he stayed with me for 3 years during the summers, and he programmed everything, all the equations, and generated all these curves and contributed to the paper as well. So we typically hire interns, student interns. We offered him, but then Amazon offered him 50% more salary. So he sort of hesitant to go. Then I sort of encouraged him to go because always my small companies are very good actually when you're learning. So that's why I also worked in a small company, SPAR in Canada. So most of my learning is actually there because you go, you design not just antennas, because it's a small group. You have to design everything, filters, diplexers, polarizers. Not only design, then you have to go into the range, you have to make them, you have to sit with the technician. Then once the hardware is made, you have to go to the range and test it. So that's how you learn. And I think most of my learning is in Canada, I would say. And then it shows for different theta g's, you can see theta sm, theta g, you can see how you select your element spacing. So typically we want to keep it 8.7 degrees as global coverage. So we can use horn sizes of about 3.1 to 3.6. Typically for satellites, we use hexagonal lattice because it reduces the number of elements. But you have very high scan applications like 60 degrees, 70 degrees, always go with square grid because the element spacing is small, then your scan loss depends on the element roll-off. So you have lower scan losses if you go with square grid. So these are the design curves, how you select the element size based on the coverage. This is of course 8.7 degree scan angle. You can see grading lobe locations for the once you scan the black dotted curve. So if you choose too big, I think you will have grading lobes within the scan, so you don't want to do that. Up to 3.5, I think about 3.5 is good, because you can keep the grading lobes. We use about 3.2 lambda eventually, and then you can see how the gain are going to be with the directivity at 8.7 degrees, black solid curve. So on the left side, you can see about 4 dBi or so. So number of elements in this case is 469. This is how the practical phase array looks like on the bottom. You can see the phase array with 400 elements or so in a hex grid. And then you have a sun shield on the top to protect the thermal cover. And then you have heat pipes. There are LNAs there and heat pipes. And then you can see heat pipes are going to north-south panels. East-west panels. So you can see this is the digital controller. You have down conversion is done at C-band, then digital converter, digital box. So everything is a complex hardware. So if you use very wide, ultra wideband type, you can use ridge elements, or you can use bow tie elements like on the top right. You can see that, or you can say wideband. You can use. We have a multi-layer patch array. So this can cover up to 2.5 to 1 bandwidth ratio. So most applications, I think this is fine. Yeah. So there's also hybrid antenna. So hybrid antenna is nothing but it's a combination of reflectors with arrays. So people sometimes use reflector arrays, but I would say it's a bad marriage of reflectors with phased array. You never do that in space unless you have very narrow or spot frequency. So reflectors are very frequency independent. They can cover any frequency. So by making flat and using the some sort of elements, frequency selective elements, you're making them narrowband. And then you need a feed. So sometimes in spacecraft, you need a curved reflector, not a flat reflector. So for imaging type or planetary missions, I think people are trying to use, NASA is trying to use, but they don't have scan, they have only one beam, and narrow bandwidth is almost spot frequency. And for those, it might be okay. But most applications, I don't think it's, I think a lot of academic interest is there in reflector arrays, but practically, if you ask me, I don't see, at least now, too much of, they're trying to increase the bandwidth a bit, but it doesn't matter. You cannot match with reflectors, because reflectors are almost more than octave bandwidth. You cannot get that with reflector arrays. So imaging reflectors are used mainly when you have multiple beams, you want to combine them, so this is one example showing multiple beams, spot beams. When you combine them, you can do a coverage pattern, etc. So to do that, you need to defocus the, this is about 19 element array. It's defocused by about a few wavelengths. So the amount of defocusing depends on how much beamwidth you want and how many elements you want to use. If you want to use too many elements, then you have to defocus a bit more. So that's, we have some patent also, 2 patents on this imaging reflector antennas, typically used for military satellites. So I'll talk about the recent advances we did on air and ground applications. So this is starting from February 2020, or the past 6-7 months. So here, I think this is the quote from Vedas. I think I want to just keep that. People think that, yeah, we know everything, but actually we knew nothing. The learning actually comes from our ancestor. Your knowledge actually comes from your superiors or your teachers, or it has been there for generations together. So you're only there to absorb a bit and then pass it on to the next generation. So I think knowledge is for all, and that benefits all. So that's a good. So if you think that you know everything, that's a bad that's a bad starting point. I think there's always learning, continuous learning. So this is the one we did for communication on the move for a soldier on the ground in a difficult situation or war situation. So you need to communicate with WGS, wideband global satellites, which works in US at K and Ka band. It's a global satellite, so can communicate anywhere in the globe. So this is key things on the ground is, of course, the soldiers, the man pack, everything is very, he cannot carry too much weight. So it has to be very lightweight. At the same time, it can communicate with 20 and 30 gigahertz, the transmit receive. So what we call it is a pedal reflector. So these we made out of 6 pedals. So you can see the top center is a pedal. They're identical. You can 6 of them you can remove and pack them and carry in a briefcase. Then it has also, then you can install that very easily. There's a common structure here, circular structure in the middle, where you mount the horn, and then the subreflector here. So this is actually displaced ellipsoid with a very small F2D ratio, 0.25. Everything has to be compact, and the horn can support both 20 and 30 gigahertz. And then not only that, it has to be mounted on the ground, so with a tripod. So this tripod is made out of graphite material. It's a quartz item, so it can it weighs only 1.5 pounds or so and costs only $300. Then the gimbal, this is a 2-axis gimbal, so you need to scan them. Our scan is plus minus 90 degrees in elevation and 360 degrees in azimuth. So we have a gimbal, quartz gimbal as well. So it's about $500 or $560, very, very cheap. It's a 2-axis gimbal, and it can give you a controller box as well. So you can just dial in where you want to scan it, will scan it. So everything is very lightweight, 10.1 pounds. So key constraints here is mass, cost, and stowage. So all these things are important. So we presented this to our AFRL customer, Air Force Research Labs customer, who manages this program. So they're pretty happy with that. And right now we're making a prototype which should be done in the next month or so. So this is the compact USB. So this is, they wanted 1 gigahertz to 60 gigahertz antenna, and they want within 24 inch by 24 inch. So typically when you talk about ultra wideband antenna, you talk about some sort of Vivaldi type elements or array type elements. So typically they give 10 to 1 bandwidth ratio or 20 to 1 bandwidth ratio at the most. And they need thousands of elements to meet the gain requirement at 60 gigahertz. So this is very expensive, and this is non-practical on the ground. So this is also for maritime and for soldiers to communicate with the aircrafts, and for maritime satellite communication as well at UHF to millimeter wave. So for it has digital TV, 2.5G, 3G, 4G, 5G, and 6G, and it has very high capacity, 100 gigabits per second. So used for, it has different waveforms. I can't talk too much about the waveforms, but it should support new waveforms which are being developed. So one antenna cannot support that. So what we did, we call it segmented antenna. So you have 3 antennas here. You segment the frequency. 1 gigahertz to 8 gigahertz is one that is provided by the low band antenna, we call it. You can see the rigid horns here. They're quartz items. Then 8 to 20 is provided by a high efficiency horn. It's a smooth wall multimode horn, no corrugations. And then the 20 to 60 gigahertz is provided by ADE type reflector design. Center fed, that's about 12 inches or so. So with that, you can see the directivity response on the right side. So minimum you get 6 dBi at the lowest frequency, 1 gigahertz, and highest frequency where we need most of the gain, I think you gain about 44 dBi directivity. So these are the 3, and it's mounted on a tripod and a gimbal system so that you can move them around. So our spec was 50 pounds, and we made it within 45 pounds. Instead of 24 inch by 24 inch, we can fit within 19 inch by 19 inch. So it's very low cost. It doesn't cost too much. So vehicular antennas, we just had a contract from US Defense to build next generation missiles. So they're very powerful, and lots of them. It's a 30-year program, and we just signed $13 billion for development phase, and the whole contract is almost $100 billion. So there are a lot of missiles, and what was different for this application is the antenna specs are very tight. They want more gain over larger coverage compared to the previous Minute Maid 3. And then the stringent phase variation. So I can't say the spec, but phase variation spec has tightened by 10 times compared to what it used to be. So that's very significant. So what you see on the middle two curves is the red curve. What was the design before? You can see some dropouts of the red curve, both in the pitch plane and the roll plane. So what we did is, instead of CP, we used LP initially, and then we made the two patches. Two patches are opposite to 0 and 180 degrees. So we made them opposite pole. One is VP, other is HP. So that when they interfere at 45-degree plane, so they don't, at 90-degree plane, you won't get deep null, so you can avoid that. So that was the design initially, but then suddenly they wanted even more stringent phase requirement. They want to go from there to, on the left-hand side, what you see, almost no phase variation. And in the azimuth plane, that is very important. So for that, we have to come up with a new design. So you can see on the right-hand side, the missile body, what we did is actually we did, two-element array. So we actually made a mock-up and to make sure that our simulations are accurate. So then we measured, and you can see the measurements versus simulations, both in amplitude and phase. So measurements are in blue curve, simulations using CST is in red. That includes the spacecraft, body, etc., everything. So pretty good agreement. So now we know that the way we simulate are very accurate, so we don't need to do any breadboard, so we can directly go into. So then we improved from 2-patch to, we call it a sector antenna. So it's made out of 6 sectors, you can see. And good thing with that is the sector is not any direct, before dielectric patches are used to be there. So no dielectric, so it reduces the mass. It's a reduced size waveguide. So input is, you can see the input here. So there's no BFN for the sector. So you minimize the losses, you reduce the mass. So basically 6 sectors are combined together through cables and etc. So when you do that, actually you get very good azimuthally amplitude and phase are very uniform, and it meets the specs. It exceeds actually the specs, and also lower cost because patches are, if you make a patch array, then you need to have, each sector should have a BFN. So that's not possible. So this is, we started, this is covers both L-band and S-band, 3 frequency bands actually, L1, L2 and S. So this is what we did is for L1. Now we're trying to improve it to combine the same sector to accommodate L1, L2. So, and then S-band will be a smaller height sector. So we actually manufacture one sector covering both L1, L2 and S-band as well. So this is how it looks like. So you end launch with a waveguide, rigid waveguide to get the bandwidth for to cover L1, L2. And then 6 slots, you offset the slots to based on your power distribution, what you want. And you don't want to add extra weight to put an absorber at the end of the last slot. So we basically try to dissipate all the power through the last slot so that we can avoid the absorber at the end. So that's how it works. So dielectric we don't need because it's advantage not to have a dielectric because temperatures when it's launched, it goes pretty high, almost 1500 degrees C. So, and then this type of manufacturing is insensitive to tolerances as well. So this is how it looks like. You can see on the left side azimuth pattern, which is want to be uniform. You can see very uniform. At the nose cone and behind the vehicle, you don't need any coverage, so we can allow. So our spec is about 85% coverage, and we exceeded that very easily with the spec. And the gain is also improved by more than a dB because you don't have sector losses. So this is another program, Protected Forward Communications. We are working for the last 1 year on this one. So main thing is for the soldier on the battlefield, he needs to communicate with aircrafts, he needs to communicate with satellites, he needs to communicate with his local area as well as headquarters. So there are different radio communications you need, and the soldier is should be able to carry it for these different radios. So the one we are designing is air and ground applications at K-band. One is communication on the move, PenCap, which is for UAVs and aircrafts, and bunker antenna for the ground. So they're all omnis. PenCap has 2 pi steradians, bunker antenna has 4 pi steradians, and it has some complications also in terms of deployment. You should be able to stow and deploy easily. And then communication at the heart needs high data rate, so we use 10 by 10 phased array. So this is the PenCap antenna for UAV. So it's almost the size of PenCap, very lightweight, and weight is only about 30 grams. So you can see on the right side, it's a patch. You can see it's with the 45 degrees truncated corners of the patch in 45 degree plane to generate CP. So a single feed probe can generate CP. That's simple. Then it has a Rexlite radome on top. So it's bonded together to the patch. And then it's attached to the ground plane. You can see on the white lines is the ground plane. So ground plane is shaped because you don't want any, initially we designed without some ground plane, but then they wanted the back lobes to be at least 15 dB. I think we are providing front to back ratio of 23 dB now by shaping the ground plane. So everything is like 1.2 inch by about 0.8 inch or so height. So about 30 grams in mass. So we sort of gave them 2 antennas. Right now they're doing some field testing to make sure that if we have to change, we change the dielectric material. We have to see whether it withstands after a couple of flights. So these are the measured patterns. Simulated is because supplier has given 2 dielectric constant ranges, 3.55 and 3.66 epsilon r. So we simulated both. One is the red curve, other is the solid blue curve. And then we made 4 antennas, and you can see they match very well in terms of return loss, in terms of our frequency is 21 in the high side, 21.2 to 21.5. So we get decent return loss and proper gain as well. And you can see the Rexlite on the bottom on top of the copper element with the shaped ground plane. So this is on the middle, you can see on the bottom how it is mounted on the range for testing. So testing of these omnis are not trivial. So it's you have to take care of the ranges as well carefully. And we measured actually in the both forward and backward directions. So we got very good match with the simulations. So other one is a bunker antenna for manpack. So this frequency is, initially it was 20.2 to 21.5. But when they saw the performance, they wanted to use KU band as well, up to K band, up to KA band. So it covers very large frequency band from 11.5 to 30 gigahertz. So the element is very simple. It's inverted F. So all these designs, you want to keep the antenna very simple. At the same time, you want to make it compact and low mass. So inverted F, everything is metallized, and it is bonded to the radome with a echoes of material. it's bonded on. And then your ground plane has to be minimal because this is, you have to cover 4 pi steradians. So we did that. So when the soldier is lying down, so it has to fold like this. So you can see on the right side, top right side, that the blue cap is actually the antenna, very small, and it's supported by non-metallic Rexolite type handle structure. And then you have a handle here which goes between the 2 stops, 2 blue stops. So one is deployed and other is when you go completely unfolded, then you hold the handle and then move it to the next stop. And in between you have a conduit. So conduit provides the flexibility when you fold and unfold. And the region between the conduit and the support has to be sealed for dust and snow and other environmental conditions. So some precautions have to be taken. And then this, you just have to flip this handle, flip this stop, and then remove that. I think I show the deployment on the other side. So when it is completely unfolded or deployed, you can see the antenna is above the helmet of the soldier because it cannot be very close to the head to meet the RFI requirements. So pretty good agreement, simulations and measurements. Only thing is you have to take care of all the materials, everything properly. So when you do that, I think you're bound to get very good agreement. So I think some deployment here I want to show. So that's it. So there are 2 stops there, and then it's in the unfolded configuration. Then to fold it again, you move it and other stop, and then use the clip to most of the components here are 3D printed to make it cheap. So these are the measured patterns, front and back directions. This is the K-band phase array 10 by 10 I talked about. So if you, I think we choose the case 2, case 3. So case 1 is when you have, say 10 by 10 is 100 elements. So your down converter and digital BFN, you need 100 inputs. So that's very large. So we want to reduce that. So then we tried 4 by 1 initially. It has its own passive 4-to-1 combining network. You can reduce the number of LNAs, phase shifters, attenuators, and number of inputs to the down converters and BFN from 100 to 25. But then you have problem with grading lobes. So then we selected case 3, where you still have subarrays, 2 by 2, but then each subarray has LNAs, phase shifters, and attenuators combined through 4-to-1 BFN. And then at level 2, you have also phase shifters, attenuators, and LNAs. LNA is basically amplifier to boost up the signal. And then your number of inputs to the down converter and BFN is limited to 25, not 100. So these all trades, when you do this, you have to do it very fast. So we didn't spend too much time, couple of days, hand calculation, show to the customer. The trades why we selected 10 by 10, we have to tell them. So when you go to, we talked about 3 configurations, case 1, case 2, case 3. So case 1 and case 3, almost the same. This is when the beam is scanned to 60 degrees. You can see the black curve for both cases matches very well. And then the case 2, which is when you don't have subarray amplifiers and phase shifters, so you can see how the scan beam suffers in terms of gain. And then your grading lobes come within the coverage, because now your subarray spacing is 2 times that of element spacing. So that's not desired. So any phase array you build, you always have a dummy row around it. If it is 10 by 10, we use 12 by 12. In this case, I prefer actually 2 dummy rows, but since the size, mass, everything is important, we I designed it only with one ring. So these are terminated in internal loads. And that way you don't have finite array effects from edge elements. Edge element behaves almost, not exactly, but very close to the central elements. So that way you don't have any problems. Some patterns here. So here we need to scan up to 70 degrees. So very wide scan, so we can do that, no problem. So actually we measured these arrays and they're exactly some tolerances. I think some frequency shift is there, but this is build 0, so we can improve that. Some uncertainties on dielectric materials and bonding material, so we need to figure it out. So this is the advanced ground antennas. Air Force has about hundreds of ground antennas varying from 2.3 meters to 15 meters. So they want to replace all by adding, currently they work at the Ka band and the S band, L and S band. So they use frequency selective surface, L and S band on the top, where frequency selective surface is transparent, and Ka band, it's reflective to Ka band frequency. So Ka band operates in dual reflector mode, and L and S band operate in prime focus mode. So now I think they want to add 6 or actually 7 additional frequencies, C band, X band, transmit receive, Ku band, transmit receive, lower KT band, and then upper Ka band, and some tracking beams as well. So when you have so many bands, of course, you cannot do that with FSS. I think they went to other vendors before and they said it's not possible. So when they came to us, then we looked into it and said, yeah, probably we can do. So we removed the FSS, we removed the struts here, you don't need all that. So on the right side, you can see, so every trick is basically on the feed array here. It's a multi-band feed with coaxial rings, concentric coaxial rings. So it has a subreflector. So we remove actually all this thing from the current antennas. We use the main reflector surface, and we actually fill in the holes where they have the struts so that you can get the improved performance. And then we remove these Ka-band horn and then insert this new feed, multi-band feed with its own subreflector to support it. So this provides actually 1 dB better gain compared to the existing bands, because at L and S band, you don't have this loss of long cable. I think this is a old design, probably 30 years old. So now technology is there to develop the multi-band feed. So it gives about 1 dB better gain, and also gives you flexibility to add the new frequency bands. I don't want to go through this. This is how the feed array looks like. It's not that simple, but we have completed the design. We have to show it to the customer. Right now we have contract to refurbish 5 antennas to 5 meters and 3 5.5 meters. Some performance parameters. So this is the experimental satellite at, we talked about congestion at satellite geostationary orbit. So this is the experimental satellite we did a couple of years back. It's being launched now. So what it has, when we started, they don't know the orbital locations. It could be anywhere from 80 to 120. So what we have to do is we have to come up with a simple design so that it can accommodate all the orbital slots. So what we did is to minimize the, if you do design for each orbital slot, then the coverage becomes very large and then your gain drops. So what we did is use the pitch biases of each satellite so that we can move it around. So with waveguides, different sets of waveguides. So that way we created a composite coverage. You can see all 5 orbital slots, how the coverage area over conus is going to be. And we used only 2 horns to make it simple and cheaper. So these are V and W band. It supports V and W band. So you do that, and then we rotate by about 12 degrees or so to orient properly. So then you get an elliptical beam like this. So, and very simple. And we actually qualified everything, space qualified. And on the ground, we use a 24-inch reflector. So reflector patterns, I think there are 5 ES ground stations here, and covering from Florida, Rome, New York, Colorado Springs, Colorado, Kirkland Base, New Mexico, and Tacoma, Washington. So depending on, one is wet region, other is dry regions, other is medium rain regions, etc. So Eglin, Florida is the most rain region. So we not only monitor the copal signal, but we monitor the crosspole too, to see the discrimination and how much, nobody knows how much is atmospheric attenuation. So we develop this over the next couple of years and then build the payloads. Actually, we are building payload already now. I think we just got a contract so to develop, we call it Whiskey T. So BNW bands. So that's the design we have. So 36-inch ADE type reflector. You can see the feed assembly. You have a high efficiency horn, septum polarizer. Then you have to generate the CP. So we need only one sense of circular polarization. So we load it at the port. Then you have a diplexer to separate V band and W band. And then we have a 4-port test coupler to be able to do system level tests when everything is integrated together. So, and then you have receive a W band RHCP and transmit V band RHCP. So contoured beam technology, we talked about. Shaped reflector is the way to go compared to conventional technology with a parabola with multiple feed, because this needs 2 antennas, one for transmit receive, and BFN is limiting the design. So whereas here there's no BFN, you shape the surface of the reflector to generate any contour you want, whether shape of India or shape of US, and single horn, OMT, some 2 diplexers, you can get a transmit receive. So these are some satellite, I think I'm almost done, a couple of charts more, and this is how the satellite looks when it's deployed. All antennas, reflectors are deployed from east and west panels, some on the native panel, solar panels or north-south directions. And when it's stored, you can see all the reflectors are stored in a compact package. And then you can see on the bottom, this is the coverage for BSS satellite, broadcast satellite service for CONUS, where we need that KU band. Rain attenuation is very important, very high. So on the Florida, you can see the red. It's very high. Rain's very high, almost 10 dB more than Midwest, or let's say gain. So so you provide more gain it's needed, less when it's not needed. So that way you can change the gain by almost a factor of 10, so that your link margin is maintained constantly across all. So if some Florida guys, when rain's high, if they don't get the TV, then they'll complain and change, go to another satellite subscriber. So that's important for operators to be able to maintain 99.8% availability for everyone. Some hardware. Deployable mesh reflector. This is, we talked about mobile satellite service, where we need very large reflectors because they want large gain. So only way to get is use like 12 meters or even 20 meters reflectors. So how you deploy these reflectors through mesh? You can see Northrop Grumman, we have one design where we deploy into small space, what you see on the top left, then it slowly folds into. So it has both the top mesh and bottom mesh to support the top mesh where it's reflecting through tension rods. And then whole package is, it packages when you, I'll show the picture a bit later. And then other design is instead of 2 meshes, it has top mesh. Harris has this design as well, which is equally good. It has a hoop truss instead of and then tension ties to hold the front mesh in shape. So, and the mesh is made up of gold moly wires, very 1 mil wire, gold moly. You can see on the bottom right. So it has typically 10 openings per inch. So if you go to high frequency, of course, you need more openings per inch. And this is the video to show the complexity of the antenna. Mesh reflectors. It's not just RF, it's all mechanical as well, and systems aspects as well. So you need to consider all those. So after 2 weeks, it's going to solar panels are deployed, and now the antenna is getting deployed. So we built the reflector, and NASA made the feed, and they integrated together. You can see the red, black cylinder is what the mesh is. Now it's slowly deploying. It has to be done very slowly. This is called SMAP, Soil Moisture Active Passive Radar. It's 680 kilometers above the Earth, and it creates a conical swath. So you can see it rotates around at 15 RPM, about 35 degrees conical angle. So reflector rotates in one direction, and spacecraft have to rotate in another direction to maintain the balance. You can see the swath now on the. So its purpose is mainly to measure the soil moisture content and how the icebergs in the North Pole are depleted. So they're going to measure that. The swath diameter is about 1,000 kilometers. Okay. So we talked about high capacity satellite. So what's the advantage of high capacity satellite? You can see on the left hand side the CONUS coverage. So if you fill that with high gain spot beams, about 0.6 degrees in this case, and use several of them, probably about 60 of them. And then you divide the 500 megahertz channel into 4 cells, 125 megahertz each, and keep reusing them. Like cell 1 is on beams 1, alternate beams 1, 3, etc. Cell 2 on 2, 4, 6, etc. Cell 3 on 9, 10, 12, 14, and cell 4 on 11, 13, etc. And try repeating that cell structure over 60 beams. So then you have 60 beams and 4 different cells. So frequency reuse factor is 60 over 4, which is 15. So you get 15 times more frequency spectrum. So 0.5 gigahertz has become 7.5 gigahertz. That's where you get your capacity mostly. And secondly, since your beams are small, your gain is more. So your transmit gain, receive gain are going to be about 15 dB each more. So almost you get 30 dB more compared to both ways, uplink and downlink. So that's where you get most of the capacity. This is only 60 beams right now. Right now we are doing about 500 beams to get 1 terabits per second capacity. These are different frequency reuse schemes. You can 4-cell reuse schemes, 3-cell reuse scheme, 7-cell reuse scheme. So typically 4-cell is optimum between getting good isolation between reuse beams and at the same time getting a good reuse factor. So for these you have to use multiple apertures. Why? Because if you use a single aperture, then you have to use, all the beams have to be very tight, adjacent to horns, because you need certain overlap between the beams. They're in the range of about 1 wavelength or so. I think you have seen this curve before. So whereas if you use 4 of them, you can go up to 2 or 2.2. So you can get almost 80% efficiency. So gain will be very high, and then your isolation between the beams are going to be high as well. So you can probably refer to this paper if you're interested in. So this is the MBA for local channel broadcast, probably this most difficult design I ever did, because here whole DirecTV wanted to, they have national channels covering ABC, NBC. This was many years back, probably 20 years back, CBS, etc. But most of the people want to hear the local channel news. So ES is divided into 216 DMAs, they call it designated market areas, based on population density. So, and also priority. New York is number 1, Los Angeles is number 2, etc. So you can see that a lot of congestion on the East Coast, and on the West Coast, it's not that much. So you need small beams on the East Coast, and not only that, you have rain factor also, high rain in the East Coast. So based on that, you need narrow beams, and so 4-cell reuse, if you use, you can see the colors of the beams, they're reusing the same frequency. So beams are changing, spacing between the beams are changing, and how you combine these DMAs together into one beam, you need to figure it out. So if you start doing software through software analysis, you never complete. So that's what happened to other some of the other people. I think they're taking too long, 3 to 4 months. So they came to us, can we do quickly? I said, okay, we'll look into. So that's when we developed the Gaussian beam analysis. So it's I think published in IEEE, both the transactions as well as AP magazine, I think 2 or 3 papers. So that they have been used by industry throughout now, Europe as well as other companies. So that gives you exactly how to design very quickly through probably instead of 3 to 4 months, we can finish all the design in less than a week. So that's what we showed. They want only 60 DMAs, top 60. Actually, we covered initially 160 DMAs. They're pretty happy, but during the contract, we actually covered all 216 DMAs. So this was very, sometimes you have to do some quick sort of analysis to complete the design. So this is some GPS work with phased array we did. It needs a triplexer to cover L1, L2, L5. And then the element you can see on the left side border. So it's a lightweight element. So you can see the polarizer, how it is shaped to generate CP. So everything is, and then there is a triplexer also behind each element, within the space of each element. So it's a 37 element array. It provides L1, L2, L3, L5 signals. So both spot beams as well as coverage beams, global beams. So some scientific mission antennas I won't go through, but you can refer to mass reconnaissance observation. This is a 3-meter ADE. Bottom is Galileo reflector, 4.5 meters. So it didn't deploy when it's launched. It took almost 2 years. They have to take it close to the sun and heat it up and then shake the spacecraft. Then it deployed. By then, I think all the fuel is gone. So it's almost useless. But I think right now they prepared they know what exactly went wrong, and they repaired it, and they flew the 2nd generation Galileo Voyager mission as well. 3D manufacturing. This I want to show because everything is related to nowadays cost. So you cannot go your conventional methods of manufacturing. So 3D manufacturing, both metal and dielectric. So this is the SLM machine I think we use. It's very good. So it can do metallic, of course, we want mostly metal for the space. So it can, you can use aluminum, silicon, magnesium powder, it comes. And then you have a roller, which basically puts in very planar. And then the piston actually starts at a high position, and then forms one layer. It's very thin layer, microns thickness. So then the laser actually cuts it to any shape you want. You can see on the middle, you can see the shape of the object being fabricated. So I think after we build actually this right side a filter, actually bandpass filter. So you can see the simulations versus measurements. Pretty good, but simulations we assume 6061 aluminum, which is very good. But this aluminum silicon magnesium alloy is a bit lossy alloy. So that's why you're losing about 0.1 dB more loss. But the rejection you can see reasonably good. So there's some, we're looking into more improved powders. So a lot of metallurgy research is going on to get powders that are close to 60-61 aluminum, so that we can manufacture very cheap. And the bottom one is basically made out of actually dielectric, and then it's electroplated on the top. So this is an array of many elements at very high frequency. So trend is, I think, towards, there's some limitations, but I think technology is developing fast towards 3D manufacturing. So this reduces the cost and speeds up. So some measurements, I think time is over. So what I want to show is actually antenna. You have to do thermal tests, you have to do thermal vacuum tests, you have to do high power tests, you have to do passive intermodulation tests like what I shown here. If you don't meet the spec, you have to do functional tests, radiation patterns, of course the mechanical vibration test, acoustic test, and finally when you integrate, you have to do EMI, EMC test. Then only your payload is qualified. So here's something about passive intermodulation. We talked about transmit channels, number of them. So when they beat each other, they generate high order harmonics. So if the harmonics fall in the receive band, so that's it generates PIM. So your PIM has to be very low. So you have to do very high filtering. That's not enough, but you have to take care of PIM is a nonlinear phenomenon. So you have to take care of the joints. You have to metal to metal joints. You have to have very high pressure between them. So any loose joints with high power is a big source of PIM. So you need to avoid that. So you can see some measurements with number of cycles we've gone through, hot and cold cycles. You can see the PIM levels in blue, actual levels, and the worst case levels, and the average PIM level in red. So our spec was minus worst case, average PIM spec is minus 127. I think we met minus 140 or so. But this you have to do in clean chamber, so with the no PIM. So lot of this test costs about 150K. So we want to avoid that. So all the design, I think you have to over design to PIM. And when you want to test these antennas, you have to make sure you have all these test ranges. We have 19 of them, 150 by 50 foot planar near field, 2 12 by 12 planar near field, 1 bistatic range to measure the FSS and some materials like blankets, etc. And then spherical near field to measure bicone type antennas, which is important. Compact range, 6 foot quiet zone. Anechoic chambers, we have few of them to measure the feed components and horns, etc. So this is some observation about academic training. I think my sort of, I was asked to put in this by somebody, so I said, okay, I'll put some charts and tell my views about academic training. I think seems to be a significant gap between academic training versus real world engineering. It's not just, it's throughout the world. I don't know about India, probably maybe slightly a bit more than US. US, I think we try to collaborate with universities and small companies a bit more. So the question is, are the universities providing the proper training for future engineers? So I talked to some of the students. They said, I asked them what they use. They said they use HFSS, sometimes CST, but very rarely FICO. So because most of them are doing some patches, etc. So in real world, I think typically you need to use Stickrus, Grasp, and SHAMP software, Machine, Cobra, CST, Savant. Savant is the one for aircrafts we use quite a bit. Spark 3D, that is for multi-action analysis. So there are a lot of other software, and I'm a bit surprised that the type of teaching, I think, given in academic universities is mainly through HFSS, which is probably limited in terms of applications. I mean, that HFSS is good software, no doubt about that, but there are other softwares which are being heavily used in the industry. So they need to be trained as well. So real world, I said, the horns, reflectors, spacecraft, aircraft, ground antennas, they all need some reflector analysis, some phasor analysis, some horns analysis, etc. So India really has a great talent. I think people are very analytic, and all the students, and they want to learn more. I think they have the right attitude, and they have also a luxury of having large industrial base. ISRO has, DRDO has, ground observatories have, RRI, Raman Research Institute, TFRL, Samir. So with all these industrial base, I think my sort of suggestion is for the universities to collaborate with them. And actually the other way, I was telling industries also, ISRO guys and DRDO guys to collaborate with them. So that's the way it works. And that's very important, I think, university industry collaboration. On the right side, I show a picture. What we have is a mentor prodigy program. So every year we get, we are the mentors, and we have Prodigy, which is a small company. And then we also take 3 interns from Cal State, California State, Los Angeles University. So you can see the picture there. On the left-hand side is Professor Liu. I am in the middle, and then the 2 students, and then company CMI on the right side, and CMI employees, which are our Prodigy. So idea is to train the students. So once is trained, they come in summer, and we pay them, and they work with us, learn, and then they come like 2-3 summers. And then after that, we absorb them as employees here. So because we know how they perform, and most of them, sometimes they're absorbed by other industries as well, but most of them remain with us. So that's proved to be very good actually for us for the last 4 or 5 years. I think we hired about maybe about 10 to 11 graduate engineers. So I think this is the last chart conclusions. What I want to say is antenna is a very exciting field to work and innovate. So if you're a student and if you're thinking what to do, which area to go, I would suggest to definitely look into antenna. I think it's more exciting than any other field, because every day is new challenges. So no design is identical. So every time you have to come up with new designs. So to do that, you need to understand the basics. So learn very well from your teachers, and what you learn, you need to apply. And then you need to, once you go into engineering, join an industry or so, then you have to develop some concepts and out-of-box ideas. Don't just copy what other people have done. So you need to improve upon that. Acquire critical skills. So hardware knowledge is important. I always stress on that one, because if you can do a lot of software things, but when it comes to, you cannot design hardware through software. So you need to have certain knowledge about hardware, what type of hardware to use given the application. Of course, once you come into a couple of years experience, you will know about it. And you need to know the mechanical constraints. Manufacturing, I think you need to know the limitations. System engineering, I think you need to work with them. Unless you know the system aspects, it's very difficult to design proper hardware. And then you need to work with customers, because sometimes you cannot impose on what you think is right to the customer. You have to understand them very well, and you have to give the right design to them, which works. Also work with passion. It makes very big difference. So every day you go to college, you go with a lot of enthusiasm, and you want to learn. So even now, I think when I go to work, I go with a lot of enthusiasm to sort of learn something new and implement as well. So that makes a big difference. Innovation should be daily routine of engineers. So without innovation, I think there's no progress. So I think we always need to think on how to improve. So engineers need to innovate, and the researchers need to publish. I think when I put this chart, I think some of the academicians didn't like it. So basically I said, that's the nature of things because engineers have to innovate. I mean, for us, I think engineers publishing a paper doesn't give us good weight. So you need to innovate and develop the products. So publications are okay, but whereas both are important. I'm not saying that publications are not important. They're also very important because they lead to, but if you're an engineer, I think you want to innovate. So this is the quote from innovation distinguishes leaders from followers. So when you start, you want to be follow somebody, but one mentor or somebody. But once you acquire certain status, middle-aged career or so, you want to lead, and that's distinguishes innovation. So you cannot be a leader unless you know how to innovate. So that concludes my talk, and I leave with the one on the B-2 bomber. I think
the B-2 spirit. The B-2 was originally intended to carry nuclear bombs deep into Soviet territory if the Cold War had ever turned hot. Its shape, paired with the plane's stealth systems, would enable it to be undetected by Soviet radars. The B-2's long range meant it could fly deep into enemy territory and return home. With the collapse of the Soviet Union and the end of the Cold War, the B-2 has been used as a conventional bomber. It made its combat debut during the Kosovo War in 1999 and has since flown sorties in Afghanistan, Iraq, and Libya. More recently, the B-2 has been placed in bases in the Pacific as part of a strategy to deal with potential threats from North Korea. Here's why it's one of the most feared aircraft in the world. The B-2 bomber was shown to the public for the first time in 1988, just before the end of the Cold War. Its stealth capabilities were virtually unmatched. The B-2 can carry 16 2,400 pounds B-83 nuclear bombs, but its official limit of 40,000 pounds of ordnance means it can carry a massive amount of precision-guided munitions. The B-2 has a max range of 6,900 miles on a single tank, but aerial refueling can keep the bomber up indefinitely. On one bombing mission, two B-2s flew a 34-hour round-trip mission from Missouri to Libya and were refueled in the air 15 times. Each of the current 20 B-2s in service are named after estates. Here, the spirits of New York can be seen at the British Royal International Air Tattoo in July of 2012. The B-2 is a flying wing aircraft, so it has no fuselage or tail. This means it has low drag, high structural efficiency, and generates more lift than other fixed-wing aircraft. The B-2's max speed is Mach 0.95, or 630 miles per hour.
I think that's it. Any questions?
Sir, there are some questions from the participants. So we will share the screen, sir.
Okay.
We'll share the questions now.
Should I close my presentation?
Yes, sir. We'll now share the screen.
Okay.
Sir, is it visible?
Yes. Yeah, I can see.
Scrolling.
Okay. So somebody speaking?
No, sir, no.
Okay. Why don't the participants speak, ask their questions, and I can respond? Or you want to respond to these questions?
Sir, they have posted the questions in the chat box.
Okay. Okay.
So these questions we have shown over here.
Which types of antennas are popular and effective in aircraft design? So it's a very broad question, but we use monopoles quite a bit. We use blade antennas quite a bit. We use phase arrays quite a bit. We use reflector antennas. So it depends on the application. Typical aircraft has about 50 or 60 antennas, different antennas. So you have seen the last time B-2. So old aircrafts, I think they have monopoles sticking out. So for B-2 type aircraft, I think it has to be stealthy. So nothing should be visible. So no metal, nothing. So everything has to be So everything is hidden. So it depends on application. Some UAVs, you can have patches, you can have monopoles, you can have some slightly high gain antennas, etc. So it depends on application. So type of aircraft, is it military aircraft or it is commercial aircraft? Commercial aircraft also different communication antennas. So mostly monopoles, blade antennas, I think they communicate quite a bit low V band. So it depends on the application. Oh, okay. Second question is, can segmented antenna be designed in planar form? Answer is yes and no. It depends on, probably it can be designed in planar form, but when you design the planar form, then you need many more elements. So here the way we design segmented antenna is mainly low cost and lightweight. So to do that, I think you cannot have planar arrays. You can design if, for different applications, but for this application, 1 gigahertz to 60 gigahertz. So we have chosen simple design, which is lightweight and low cost, which is made up of 3 antennas, basically. They can be all these, each antenna has 2 ports, dual polarization. So they can be used as MIMO, they can be used differently. So yes, answer is yes, it can be designed in planar form, but cost and mass will go up very drastically. So noise is an important consideration in antenna, how it is tackled in the antenna design, especially in the reflector design. Yeah, good question. So noise is of course important. So we have to make sure that there are 2 types of noises. One, I think outside the band, outside frequencies, I think you want to reject them. So to minimize the noise. Secondly, the noise, you want to maintain, I think, minimum signal at the receive side, which is very sensitive. So we have filters actually as part of to reject different frequency bands. So not just only transmit to receive, but other bands also. So to minimize the noise. So I think transmit side is okay, but receive side is more sensitive. That's where you have most of the filtering and minimize the noise between various different frequencies coming from outside. Okay. Can you use planar metamaterial antenna for satellite applications, or can we use compact size antenna for satellite application? Don't know the intent of the question, but metamaterial antenna, so far, it depends on the material. If the materials are characterized properly and they can use in, right now, I think no metamaterial antenna is there in space because of the reasons I mentioned before. Extreme temperatures and wide bandwidth properties. People have done it very narrow band, so I sort of it's still, I think, in the development stage as far as I'm concerned. But the satellites, yeah, answer is no. Metamaterial, you cannot use metamaterials, at least currently in space. Maybe aircrafts, I think people are trying to use it, but we have to see how we can implement them in the practical design. Or can we use compact size antenna for satellite application? So compact size is you need a lot of gain from the satellite antenna. So size, it depends on your gain requirements. Compact size, if you want to use for omni type antennas, maybe you can use, but not for high gain antennas. They're typically reflectors or phase array type designs. Can we replace this parabolic dish with any planar antenna? Well, people try to use that. Reflector array is mainly for that, but you limit the bandwidth. So I think my straight answer is no, because parabolic dish has a lot of properties. It's wideband. It doesn't, not only wideband, it cannot give any dispersion, phase dispersion. So I think that's a good property. Why spoil the good properties of reflector antenna and make it planar? And the planar also doesn't mechanically, it's not preferred, because when you stove it, you want to be more curved. So I think mechanically also it's preferred to have parabolic reflectors. So what are the specifications to be considered, and what are challenges in designing antenna systems for space? Well, specifications, I think I mentioned. So it has to, of course, it has to meet the gain. It has to cover the very wide bandwidth, the transmit receive. It has to have very good cross polarization, like 38 dB or so. It has very good return loss. We don't tolerate the 10 dB or 15 dB return loss. By design, we want to have 25 dB return loss. All components together, including reflectors, feed assembly, feed components. So spec is typically 22 dB, including thermal. So you need to meet that spec. And gain variation spec will be there, and then phase center, phase variation is also very critical, and then high power handling. So all these, when you design these components, you have to make sure it handles the power coming out of the amplifiers, 2 kilowatts or so. So typically filters have narrow gaps. So when you design, make sure that you have sufficient gaps not to create problems with multifaction, etc. And PIM is also, so materials are important. Manufacturing, type of manufacturing is important. So how you connect the waveguide junctions, how much pressure you put on the waveguide, is it 10 kpsi or is it, so if you have very loose joints, actually it PIMs. So all these things are very important. Are there any dismantle and unused satellites, as the retired satellite will keep, transmit and receive the signals? Were there any programs, projects to clean? Yeah, I think it's also a good question. A lot of junk in space, because once they lose the fuel, I think it becomes non-operational. So it will be spinning around. So one of the problems is some of these spinning satellites in space, sometimes they hit other satellites, so create problems. So idea is to detect them and remove them. So they're sending special missions and to capture them and then bring back or destroy them into small pieces so that they won't affect the current satellites. So this has been going on for almost like 3-4 years now. So I think in future, I think we'll probably see how to eliminate the debris in space. So any other questions?
No, sir.
Okay, very good.
So thank you very much, sir, for a very informative session.
Thank you. Thanks for the opportunity, and wish you all the best.
Thank you, sir.
Thank you for your wonderful lecture, sir. Thank you for your wonderful lecture. Thanks a lot, sir.
Thank you. So if you have any questions, you can reach me. I think you have my email, so people can send me an email so I can sort of reply when I get time.
Okay, sir.
Thank you. Thank you,
Thank you,
Sudhakar
sir.
Garu. Excellent. Very wide coverage. Lakshmi Narayana,
Wide coverage.
Hyderabad.
Oh, thank you.
Total, I think we can't expect any, better than this. Number of antennas,
It's always
technologies,
better.
engineering. Sir. Thank you, sir.
Sir,
Thank you.
so this is Professor Mahadevan. So you have covered from every area, right from the smallest one to the multi-beam antenna, and then what sort of variations the multiple antennas can have depending on the geography of the country, etc., which needs to be seen. In fact, if you know, India is also looking for large multiple beam antenna system for guiding. We have just started off with that, but there are a lot more to be done. That is one very key area which you have really pointed it out also. And also the 3D manufacturing, which we are told is a very important area which people can really concentrate and get it done. So we had really a gamut of a lot of topics which the researchers can see at this time. Thank you very much. And thanks for the organizers for arranging such a wonderful lecture. Thank you, Mahadevan here.
Yeah, I think
Thank you.
ISRO is doing very good job. I think they're in contact with me. I think I gave a couple of seminars in Ahmedabad on multiple beam antennas, and they started like 4 years back or so. I think right now, I think they're doing very good actually.
Yeah.
Because it's limited, but they're trying to expand on the high capacity satellites, number of spot beams, etc. There's some limitations there. I think they're working on it.
Yeah, that's true. That's true. Thank you.
Yeah, thanks.
So we are winding up the session now. The next session is handled by Dr. Sangeeta Velan on the topic wearable and reconfigurable antennas in Internet of Things. Dr. Sangeeta Velan currently works as consultant of Invikara India Private Limited, Chennai. She received her BE in Electronics and Communication Engineering from Panimalar Engineering College, Chennai, and completed ME in Communication Systems from College of Engineering, Gindi, CEG, Anna University, Chennai, and received PhD from CEG in January 2017 on the design and performance enhancement of microstrip couplers. She also holds the experience of being an assistant professor at St. Joseph's Institute of Technology, Chennai. Dr. Sangeeta has over 12 publications in international journals and has presented papers in various national and international conferences. She holds a credit of 2 Indian patents and has received the Anna Centenary Research Fellowship during the PhD course. Her areas of interest include microstrip components, antennas, RF and microwave engineering, and Internet of Things. Now, I hand over the session to Dr. Sangeeta Velan.
Thank you. Thank you so much, madam. Am I audible to everyone?
Yes,
can you
madam.
And is the screen visible?
Screen?
The PPT?
No, ma'am.
Okay.
It's not.
Okay, I'll share it again.
It takes some time.
Okay. One second. Now, madam?
Yes, ma'am. It's no. Yes, ma'am.
The PPT is visible, right?
Yes, ma'am. Can you put it into slideshow mode?
Yeah, I will.
Okay, ma'am.
Yeah, now?
Yeah, ma'am. It's visible.
Okay. So after sir's wonderful presentation, it's indeed, I'm humbled to do this humble presentation. Anyways, let me share my observations on the topic wearable and reconfigurable antennas in IoT. So from my alma mater, Dr. Malti ma'am. So I'll just this will be the flow of the presentation. Let's quickly just go on. So firstly, we'll be seeing about wearable antennas. So we'll be seeing a few applications and a few designs and certain important aspects which are specific to wearable antennas, like the bending and crumpling analysis, because the antenna has to be placed in close proximity to the human body. And then about the wetness analysis, SAR, and the importance of EBG structures. And we'll be moving on to reconfigurable antennas. So we'll be seeing the importance of reconfigurability and some methods to achieve reconfiguration. And we'll be seeing various classifications and some applications. And finally, currently I'm into the IoT area, a little bit of real-time work I'm doing. So let's see how much of importance antennas hold in general in IoT, and specifically the wearable and reconfigurable antennas, their importance in IoT. So we'll be seeing about that. So firstly, wearable, in case there is any interruption, kindly tell me, right? So I'm just proceeding. So wearable antennas, as we all know, it's any antenna that can be worn by by human beings. So it could be anything, a goggle, or more precisely, it is the antenna that's embedded as a part of the textile. So these are also called as smart clothes. So as you can see, this particular woman, she is having so many sensors in her body, in her jacket. So she's having a humidity sensor, a temperature sensor, a heart rate monitor, everything is there. When there are so many gadgets, so many wearable gadgets, what do? They simply collect the information. So information, when collected, is of no use unless it is transmitted transmitted to a particular place where it is processed. Say, for example, a person is having some heart issue, so his heart rate is monitored. So it has to reach the doctor for him to see and give the updates. So for that, we need a transceiver, a transmitter and a receiver. So an antenna is an extremely important part to be worn. So with personal area networks and with body area networks evolving, I think wearable antennas are becoming more and more important these days. So where did this concept of wearable antenna start? When we see, firstly, initially the military applications, they used to carry the whip antenna. So the enemy people, they could see the whip and they could find that he's carrying a radio, so he could transmit whatever information that we are speaking, right? So in order to combat that, if the antenna is just embedded as a part of the clothing, right, so people cannot see it, it gets camouflaged. So that's where the idea initiated. And also the whip antennas could get entangled with plants and other obstructions, so it could hinder the communication. So this is the first application wherein the process started. So there are several other applications of wearable antennas, firstly for military, and then the emergency services, the police and firefighting applications, so that's very much used there. And then augmented reality, so this is an important field where wearable antennas are very much used now, because everybody cannot go to every place. Say, for example, a coal mine, so a person carrying a camera can go there, and through his wearable antenna, people can comfortably sit in their room and watch what is happening in the coal mine, right? So augmented reality is an important field where wearable antennas are used. And then navigation, obviously GPS is there. And in health applications, in health and monitoring applications, it's very much used for the patients, for the doctors to remotely monitor the patients. And obviously in identification systems, which we'll be seeing in the IoT part. So in an office, there are so many employees, so each of them having their identity card. So RFID antennas are embedded as a part of the identity card, and Bluetooth antennas. So it's very much a part of the identification system. And space exploration, as sir has very beautifully said the importance. And so this is the simple wearable antenna. So there is an inner layer, the antenna, and then there's a waterproof layer and the outer layer. So this is specifically designed for regions where the climate could go to any extreme, right? So these are some pictures. So this is a watch which is used as a wearable antenna, a goggle, and a helmet, and an RF vest antenna. So these are specifically for the firefighters. One second. Yeah. So moving on. So this is a shoe in which there are sensors and antennas. So there are huge brands which are involved in making this. And this is a finger ring antenna. However, there is an issue with the finger ring antenna. The other fingers, they could interrupt the radiation pattern. And this is a button antenna. However, the omnidirectional radiation pattern that this particular antenna produces, that could affect the human body. It could increase the specific absorption rate, and also detuning due to human body could happen. So that's about a general introduction to wearable antennas. Now, since these antennas are so important, they are deployed in so many places, is it that simple? No, there are issues in the design of wearable antenna. Firstly, the antenna has to be worn, so you cannot build a huge antenna because it has to be comfortable for the wearer. So the volume is limited. Secondly, it has to be used in close proximity to the human body, which means when the frequency detuning happens during on-body missions, because human body is a high dielectric medium, so frequency detuning could happen. And also the radiations from the antenna could increase the absorption by the tissues. So SAR should be kept in mind while designing. And when it is used for W-band applications, the antenna cannot be kept in flat position always. So it could go to a situation wherein it has to be bent. Say when you're placing it on the arm or on the leg, it has to be bent. And when you're placing it near the joints, there is a probability that the antenna could get crumpled. So crumpling is another aspect that we must keep in mind. And wetness is another major factor. Wetness could be due to small reasons like sweat or atmospheric humidity, or two big reasons like rain. So these are all the issues that we must keep in mind. So keeping this in mind, how do we go about designing an antenna. So the first important aspect is the substrate selection. So what is the substrate that we are going to be using? What is the how many layers? What is the firmness? What is the water resistance of the substrate? And after that is the conductor. So the conductor, are we going to be using a conductive fabric or a copper sheet or a conductive ink or a conductive thread? So what is the kind of the conductive material? And the next, how is the antenna going to be performing in the real-time situation? And the next is the ground plane optimization. So preferably an infinite ground plane is preferred. However, for practical realization, the optimizations need to be done, and we need to implement extra structures like electromagnetic band gap structures, artificial magnetic conductors, which will reduce the specific absorption rate and improve the performance of the antenna. And the antenna must essentially perform well when it's placed near the human body, so that must be kept in mind. And SAR, specific absorption rate, which we'll be seeing in detail, is an important parameter that must be measured. So yes, talking about the antenna substrate. So firstly, the bandwidth and the efficiency is determined by the substrate that we are choosing. So generally, textile materials are low dielectric constant substrates, which means that they reduce the surface wave losses, and the impedance bandwidth of the antenna is also high. So we can use natural as well as synthetic fibers, polymers as substrate materials. So these are a few substrate materials you can see. So in this particular experiment, it has been the parameters, the permittivity and the loss tangent have been determined using the waveguide cavity method. And these are 3 GPS antennas which have been designed using textile fabrics, right? So yes, jean is a material that we commonly use, and jean can also be used as a substrate for designing a wearable antenna. So this is a jean fabric which has been, whose properties have been estimated using the coaxial probe method. So it's around 1.7 its permittivity. So that's about the substrate. Now the next important aspect is the conductor for the wearable antenna. So obviously the conductivity is the parameter that is crucial as far as the conductor is concerned. So it is inversely proportional to the surface resistivity and the thickness of the fabric. So the lesser the thickness, the lesser the surface resistivity, the better is the conductivity of the fabric. So now that we have the substrate and we have the conductor separately, we need to look for methods to combine both, right? So firstly, there is the liquid textile adhesive. So that can be glued between the two layers and it can be sandwiched, or point-wise application if the conductor is to be specifiedly stuck at a point, and then sewing using conductive threads. And there are adhesive sheets which can be placed between the layers, and when you iron it, it gets activated. So these are various methods by which we can integrate the substrate and the conductor, right? So now we'll see a few examples of wearable antennas. So this is a simple Koch fractal tri-band wearable antenna. So as we can see, it's a dipole kind of a design. So this offers a tri-band response, and Koch fractal has been implemented. So if we see the surface current distribution, as we all know, the lowest frequency, the longest arm is responsible for the lowest resonance, and then the middle arm for the middle band, and the shortest arm for the highest frequency band. Now, this is the fabricated prototype. It has been fabricated on the jean substrate. And as I had mentioned, we can use different kind of conductors. So the first conductor is a copper foil, and the second conductor is a conductive fabric, right? So when we see the reflection coefficient responses of both, with a slight variation in the attenuation, the responses do not vary much. So depending on the kind of durability that we need for our specific application, we can choose the kind of conductor that would be suitable for us, right? So this is another antenna design. So this is a semi-loop coplanar waveguide antenna. So this is this is the basic antenna, which kind of offers a response like this. So now when meandering is implemented in the ground plane, it basically increases the electrical length. So what happens is the response shifts to a lower frequency near 1.57 GPS band, and later a parasitic element, okay, so a near field resonant parasite is included. So the length corresponds to 1.57 gigahertz. So this improves the response of that particular structure. So this is a an extremely thin Rogers material, so it's flexible and it can be used for wearable applications. Now, this is another example. So firstly, even in this, there are thin substrates are used which are flexible and which can be used for wearable applications. Now, firstly, it's a multi-layer structure, okay, as all of you can see. Now, let me tell you the trade-off that is happening over here. Okay, so first, initially, we are using a substrate and there is a patch. This is the first layer. Now, this first layer offers response at like a point frequency at 4.95. There's hardly any bandwidth over here. Now, for this, we are using another substrate and we are adding another layer with a fractal Minkowski fractal geometry. Now that is widening the band. Now I'll tell you the reason why we're going for this. Firstly, since it is variable, another layer will probably cause a slight hindrance, but the advantage over here, as I had said, human body is a high dielectric medium. So frequency detuning is something inevitable, right? So if we are designing an antenna that is going to have a very small bandwidth, if there is going to be a detuning, our desired band will not be covered by that antenna. So it's always preferable to use fractal designs and use additional parameters to improve or enhance the bandwidth, so that even if there is detuning, our preferred band of operation will still remain within the bandwidth of the antenna, right? So as I had said, it's not going to be placed in free space, so it has to be placed on the human body. So this is a measurement, on-body measurement with the wearable gadget. So it has been placed on various places like the head, the torso, the arm, and the leg. These are different body worn scenarios. And another analysis, as I had said, it cannot be always placed flat. So it has to undergo bending stresses. So if we are placing even in the torso, it has to be bent. If we are placing it in the arm, it has to be bent. So it has to be bent in cylinders of different radii. So typically styrofoam cylinders of different radii are made, and the antenna is bent on those cylinders and the responses are measured. So we need to see if our preferred brand of operation we are still able to obtain when the antenna is bent around these cylinders, right? So it is also important for us to perform the bending along different orientations, not just along the x-axis, along the y-axis, probably x plus 45, x minus 45. So it has to be bent along different orientations, because we do not know in what position the antenna would be after we move to a particular distance. So bending analysis is very crucial in wearable antennas. And the next analysis is the crumpling analysis. So when the antennas are placed near the joints, it could get crumpled. So these are the different extents to which the antenna is getting crumpled, right? So you can see the reflection coefficient response. So the lowest band is not, there's no much change as far as the frequency is concerned. There's slight attenuation. However, there is a change in the frequency in the upper band. And as far as the radiation pattern is concerned, some additional nulls are introduced due to crumpling. Right. So these are the other kinds of crumpling. So this setup you can see is a Roja cell former setup. So it can be done for different degrees of crumpling, and then the antennas can be placed there, and it can be studied for various extents of crumpling. So this is the crumpling which is performed along the YZ plane. So here we can see that the field is getting disturbed, right? So as the field is getting disturbed, as the crumpling degree increases, we can see attenuation is happening, right? And in this case, it is bent along the XZ plane, right? So what happens over here is the radiator is getting affected. So the length of the radiator is kind of getting shortened, as a result of which it's moving towards higher frequency bands. And there's also attenuation towards the worst cases where the feed gets affected. So these are the effects of crumpling on the antenna. So any antenna that's designed, if it is going to be used for wearable applications, it has to be studied for bending and crumpling scenarios. Now, let's move on to see the effect of wetness, right? So when it is used in proximity to the human body, the effect of sweat, as I said, that could be the major reason for wetness, and rain could be a major factor, right? So as we all know, water has a permittivity of in the range of 78, and the permittivity of our textile fabric is only 1 to 2. So obviously, when water is absorbed by the textile fabric, the properties of the textile will vary, certainly, right? So water absorption, how do we estimate this particular parameter? So the dry mass of the fabric, and then the saturated mass, when the fabric is completely saturated with water, so that is estimated, and the current mass is measured. So when this particular formula is done, we can estimate the water absorption. We can estimate the performance of the antenna for different percentages of water absorption. Say if the antenna is going to perform well till the water absorption is 30%. So it is to understand the performance of the antenna, to what extent the antenna would perform well if it is put to a situation where it is going to get affected by wetness. So this is an important study as well. Now, as I had said, specific absorption rate is an extremely important parameter. So it is nothing but the amount of electromagnetic radiation that is absorbed by the tissues, right? So its unit is watt per kilogram. So as such, it has to be studied over the entire human body model has to be taken, and the antenna has to be placed over different regions of the body, and the SAR has to be estimated. However, for simplicity, there are simple human body models like the rectangular human body model or the cylindrical human body model, which can also be giving us a, an equivalent kind of a picture. So this is the rectangular human body model, which is composed of skin, fat, and muscle. So these are the thickness, permittivity, loss tangent, and density details of this skin, fat, muscle tissue model. So according to the IEC, International Electrotechnical Commission, the SAR limit is 2 watt per kilogram, averaged over 10 grams of tissue. So it is important that we make this SAR assessment for all the wearable antennas that we are designing. And the skin, fat, and muscle layers, the thicknesses can be varied to see how the antenna performs in different regions of the body, and the distance from the rectangular body model can also be varied to see how the antenna performs. So this is about the specific absorption rate. And as I had said, when the antenna is going to be placed on the body, the detuning could happen due to human body, and the radiations could also affect the human body, right? So in order to prevent that, we are going in for electromagnetic band gap structures, artificial magnetic conductors. So this is a paper substrate antenna. So this is a simple monopole on top, and this is the EBG array. So as you can see in this particular layout, so firstly the antenna is on top, and then there's the paper substrate, the ground for the antenna, and the EBG layer, and with a small spacing there is the copper sheet. Okay, so this is the structure of the antenna. So as you can see, with the electromagnetic band gap, we are getting an improved response. So and also this is another work. So in this we can see that without the electromagnetic band gap structure, the back lobe, and with the electromagnetic band gap structure, the back lobe, right? So as you can see, the radiations which come into the human body is reduced, right? So this is the SAR assessment which was made without the EBG. So it was 5.77 and 6.62 at the two bands, and with the EBG structure, it got reduced significantly to 0.024 and 0.016. So this is the effect of electromagnetic band gap structure on the performance of the antenna. So yes, this was about our wearable antenna. So we just saw what wearable antenna is and about the design and important aspects: the bending analysis, crumpling analysis, and the SAR measurement, wetness analysis, and the EBGs to improve the performance. Now we are moving into the next topic, which is the reconfigurable antenna. So yes, today everybody is asked to multitask. So it's not essential if we do one task alone. So we have to do this, we have to do that, and we have to do each task at a different time. So we need to switch between from one task to the other task. So it is not only for human beings, it is for the gadgets as well. So it's for the devices as well. So when the devices have to shift from one functionality to another functionality, the antenna, say for example, today in our mobile phones, we have so many frequencies, so many operations. We have the tracking, we have GPS, we have Wi-Fi, we have Bluetooth, we have so much. So these antennas, each antenna has to perform at one specific type. So switching has to be done. So it has to reconfigure from one frequency to the other frequency, from one kind of operation to the other kind of operation. So reconfigurability has become an important aspect as far as the antennas is concerned. It is nothing but the ability to change the radiator's operating characteristics, right? So we are basically altering the electromagnetic fields in the reconfigurable antenna. So as such, how do we, what are the aspects that must be changed in order to achieve reconfiguration as far as a patch antenna is concerned? If you see, firstly, the surface current distribution, and then the edges, and then the physical structure of the antenna and the feed. So if these are the important areas which must be played around in order to achieve reconfigurability. Now, what are the methods in which reconfiguration can be achieved? So if you see, there's the physical method, and which is the mechanical method, and then by changing the material, we can achieve reconfiguration. And then there's the optical method of achieving reconfiguration. And finally, it is the electrical method of achieving reconfiguration, right? So now this is an example in which a mechanical reconfiguration is achieved. So firstly, in this is actually a cognitive radio kind of design. So there is an antenna which is sensing. It's a fixed stationary sensing antenna, and here there is a feed. Okay, and there are multiple radiators. Now, this particular circular structure, there is a motor that is fixed. So the angle of rotation is varied. So each time one particular radiator gets attached to the field. So as the radiator varies, obviously the responses also gets varied accordingly. So this is the mechanical method of achieving reconfiguration. So wherein we are mechanically rotating this particular elliptical structure, right? Now, this is another mechanical or physical reconfiguration. So this is a rollable structure, as you can see. So now, as you are rolling it, as the tightness increases or decreases, the property of the structure changes accordingly. So this changes the response of the antenna also accordingly. So these are examples of physical or mechanical reconfiguration. Now, this is the reconfiguration by material change. So there are some materials which are smart materials. So they have the ability to change their properties when certain parameters like voltage is changed, right? So this is a reflector antenna, and this is the PTFE substrate, right? So here what happens is, when a low voltage, say 0 volt, is given, the molecules are oriented vertically, and when we are increasing the voltage to say 20 volt, the molecules are oriented horizontally, right? So for each kind of an orientation, the material is different, right? And the responses of the antenna is also different. So this is the reconfiguration by material change. The next is a typical this is not an antenna, but this is a phase shifter. It's a coplanar waveguide phase shifter. So this is the top view of the coplanar waveguide phase shifter, and this is the bottom view. And here a rectangular shaped packet is etched in the substrate, and in this a W-shaped packet is etched in the substrate. And typically in this particular work, the author has filled different kinds of material in the packet, and the phase shift has been observed. So firstly vacuum, and then distilled water was filled, and oil. So the responses, the phase shift of the antenna, of the phase shifter, was observed, and as the material varied, the phase shift response was also observed to vary. So this is an example wherein we can change the material and obtain a different response, right? The next is optical reconfiguration. So it's using photoconductive materials, right? So what is an optical switch typically? So it's a semiconductor material which is incident with laser light. So when the laser light is incident, it goes to the on state, and when the laser light is not there, it goes to the off state. So when the laser light is incident, the electrons move from the valence band to the conduction band. So this is a typical example. So the advantage is its linear behavior, and there's no need of any biasing lines. However, the limitation is because it is lossy, and the laser light has to be, there's a need for an external laser source. So this is the optical reconfiguration. Now, the next is the reconfiguration by switching. So this is the most common kind of reconfiguration which is used typically. So firstly, what a switch is used? Firstly, it is to connect and disconnect certain parts of the structure from each other. So it creates different paths for current to flow each time, right? So different kinds of switches are used. Mechanical relays can be used, MEMS switches can be used, and FET switches and pin diodes. Pin diodes we'll be seeing in several examples that are going to follow. So these are about the different kinds of reconfiguration. So we all know about pin diodes. I don't think I have to go in detail about this because of the intrinsic layer that is embedded between the P and the N junctions. It's used for RF applications. So in forward bias, there's an increased concentration because of which the pin diode goes to the on state. And in reverse bias, the isolation, the intrinsic layer increases because of which the isolation increases, and it does not allow the current to flow. As simple as that. So we'll be seeing a few examples of pin diodes in the following PPTs slides. So next we'll move on to the classification of reconfigurable antennas. So now that we have seen the different methods by which reconfiguration can be achieved. So firstly, the mechanical method and by material change, and optical method and by switching. Now we'll see the general classification. However, there are multiple other classifications. So firstly, we can reconfigure the frequency of operation. Okay. Secondly, the radiation pattern can be reconfigured, and then the polarization can be reconfigured, and the final one is the hybrid reconfiguration, which is a combination of the above three or of any other kind of reconfiguration also. So the first is the frequency reconfigurable antenna, right? So obviously, as the name suggests, if we are able to either tune the frequency over a range or to hop the frequency over different frequency ranges, then it's a frequency reconfigurable antenna, right? So this is an example. So this is a reconfigurable antenna. So these dots are varactor diodes. So obviously, as the capacitance value changes, the tuning changes, right? As you increase the voltage, the capacitance changes, because of which the frequency response of the antenna is changing accordingly. And these are the inductors. So they have played around with varactor diodes near the edges. So these are the crucial places which are responsible for obtaining circular polarization. So this is a circularly polarized antenna. So we can see that the frequency, so for varying the voltage values, the capacitance values, the frequency gets shifted from 1.9 gigahertz to somewhere near 2.5 gigahertz. So there are 5 different frequencies that we could obtain. And for each frequency, we are also able to obtain the desired axial ratio for circular polarization. So this is about the frequency reconfigurable antenna. Now, the next is radiation pattern reconfiguration. So as we all know, we can just change the reconfiguration pattern in terms of the shape, direction, or even the gain. So here you can see that there's a U slot. This is a U slot antenna, and these are shorting posts, and pin diodes are attached. So there are 2 sets of diodes. The ones on the sides are diode A, and the ones on the top and the bottom are diode B, right? So by just giving different kind of biasing to these diodes, we will be able to obtain pattern reconfiguration, which we'll be seeing in the following slide. So firstly, in state 1, when no bias is given to both the set of diodes, we are able to obtain a bore site radiation pattern, both in the XZ and YZ planes. And then firstly, the group A is reverse biased and group B is forward biased. So because of that, we are able to obtain canonical radiation pattern with improved energy, okay, with improved power in the YZ plane. Now, in the next, we are forward biasing the group A and the reverse biasing the group B. So because of this, in the XZ plane, we are able to obtain improved power level as compared to the YZ plane, right? Canonical pattern with improved power level in the XZ plane. So this is about pattern reconfiguration. Now, following that, we'll move on to polarization reconfiguration. So obviously, as the name suggests, it is reconfiguring the different polarization states of the antenna. So it could be between horizontal and vertical polarizations, or it could be between minus slant 45 to plus slant 45 polarizations, or it could be between LHCP, left hand circular polarization, and RHCP, right hand circular polarization. So here here we can see a rhombic shaped antenna with a Y-shaped feed, right? And there are two pin diodes, pin diode 1 and pin diode 2, right? So by switching the pin diodes, by keeping one in on and the other in off, and the one this one in off and this one in on, we will be able to obtain LHCP and RHCP. So yes, in this particular surface current distribution, we can see that firstly, when pin diode 1 is in on and 2 is in off, we are able to obtain the LHCP pattern. And when pin diode 1 is in off state and 2 is in on state, we are able to obtain the RHCP pattern, right? So this is about the polarization reconfiguration. This is just about LHCP and RHCP. We can obtain various other kinds of reconfigurations as far as polarization is concerned. And the next is hybrid reconfigurable antenna. Before we could go to hybrid reconfigurable antenna, of late there is also notching which can be reconfigured. The UWB, the entire UWB frequency can be designed, and the notching band in the UWB range can be reconfigured. So that is another kind of a reconfigurable antenna. So hybrid, as I had mentioned, is a combination of say frequency plus pattern, or frequency and polarization, or pattern polarization, or any other combination, right? So this is an example of frequency and pattern reconfigurable antenna. So as you can see, there are varactor diodes which are introduced. So by varying the varactor values, varying the capacitance values, we will be able to obtain different frequency and patterns, right? So this is an example of hybrid reconfiguration. Now, so we'll see an important application wherein reconfigurable antennas are used. So cognitive radio is an important area where reconfigurable antennas are very much in use. So cognitive radio is a place wherein firstly we'll have to continuously look for white spaces, right? We'll have to look for spaces that are free, and once we find, immediately at that spot frequency we need to transmit and receive, right? So for looking for the white spaces, we need a sensing antenna, as we can see, and for transmitting and receiving at that particular specific frequency, we need a reconfigurable antenna, right? So in this typical application, there is a need for a UWB sensing antenna and a reconfigurable transmit and receive antenna, right? So this is an example of an antenna that is designed for cognitive radio. So as you can see, this is the UWB antenna, which is the sensing antenna. So it is fixed, so it's continuously sensing in the entire UWB range. And then there is the feed network, and then there is a rotatable structure, which you'll be seeing in the next slide. So this is one particular radiator. This is just a small example. There needs to be multiple radiators, because it's not just two frequencies that could be transmitted. In fact, tuning would be better, right? But this is just a simple example. So this is one particular radiator, and this is the other radiator. So as the structure is rotated, right, once this radiator is attached, it will transmit in this particular frequency, and when it is rotated and the other radiator gets attached, it will transmit in the other frequency. So yes, this is the fabricated prototype, right? So this is the rotating structure, right? And this is the back view, as you can see. So now initially, when this particular structure, the bigger one, when that is placed, it offers response somewhere near 6.5 gigahertz, and when the other smaller structure is attached to the feed line, it offers response somewhere near 4, right? So this is about the reconfigurable antenna that is used for cognitive radio. Now, as Sir had elaborately said about satellite applications, reconfigurable antennas are extremely important for it to rotate and zoom to a specific region. So it's essential for it to for its parameters to get reconfigured. And deployable antennas are essentially used, so which changes its shape from a small compact structure to large booming antennas in space. So let me not dwell much on this, and we can just quickly move ahead. So we had seen separately about wearable antennas and about reconfigurable antennas, the materials, the methods by which we can achieve reconfiguration, and the classification of reconfigurable antennas. Now we'll see a combination of a flexible and a reconfigurable antenna. Okay, so this is actually folded slot antenna. Okay, so this is the basic folded slot antenna, and in this folded slot here we are placing a switch, a pin diode, right? So when the pin diode is placed, what happens? There are two states, obviously. In the off state, it does not allow the current to pass through this layer, and there's a return path happening, right? In the off state, it allows the current to pass through that layer. So that is what is happening. So this is about the antenna design, right? So the antenna is designed on a flexible substrate. So this is the pin diode and the biasing. So we can see that the antenna is bent along the circumferential configuration and along the axial configuration, right? So obviously, when you're using the pin diode, you're going to be having two switching states. So when the pin diode is in off state, there is a return path, right? So it offers two paths for current to flow, so because of which it offers a dual band response. And when it is in off state, it's just the T structure, so it offers the single band response, right? So a switching between the single and dual band can be obtained using the pin diode, and on top of that, it is flexible. So this bending analysis along the circumference and along the axis is performed. So the antenna also performs well under bent conditions, as you can see in this particular graph. Okay, so the responses, the frequencies, there's not much of a shift in frequency band, and the responses are also good. Okay, now as I had mentioned, the antenna is going to be placed in close proximity to the human body, because of which an additional AMC surface is very important to reduce the SAR specifically, right? So this is the AMC structure that is being placed behind the antenna, right? And this is the response along with the AMC structure. So as it is evident that the response is improved matching responses is obtained with the AMC, which is designed at that specific frequency, right? So this is the on-body measurement and the bending measurement, which is performed along with the AMC structure. So yes, this is the SAR part. So we can evidently see from the surface current distribution. So this is the SAR without the AMC structure, and this is the SAR with the AMC structure. So you can see the reduction in the redness. So you can see that there's a significant reduction, as we had seen in the data in the previous wearable antenna slide also. So somewhere from 5.52 to point something, 0.02 something. So it is reduced to such a significant extent. So that is the advantage of using the AMC structure. So yes, we had seen separately about the flexible wearable antennas and the reconfigurable antenna, and this is the two together. Now let's move on to the application part. So just a little bit of a real-time understanding. So as we all know, IoT, the Internet of Things, is the evolving area today. So so what is Internet of Things? Just a small brief. So what could be a part of the IoT? So anything could become a part of the Internet of Things, provided it has two characteristics. Firstly, okay, it has to have a UID, a unique identifier. That particular object has to have a unique identifier, and it must be capable of transmitting its data independently without any human intervention. So if it has these two characteristics, any object can become a part of the Internet of Things. So that's about IoT, right? So the wearable gadgets that we use, so that is a part of the Internet of Things, right? A computing device, an animal with a biochip transponder, people with heart monitor implants. So everything is a part of the IoT. An object, a digital machine, a mechanical machine. So as you can see, everything is a part of the cloud, and everything is connected across the globe, right? And industries, they use IoT to enhance the customer service, to improve the decision-making capabilities, right? So as far as IoT applications are concerned, firstly, is used in smart home applications. So wherein every part of the home, lighting system, the ventilation system, the gas, stove, everything is connected in a single app. So everything is able to transmit its own detail, and it's very much used in the industries to set alarms. So there are so many processes that take place in the industries, right? So there are machines, there are sensors, there are raw materials which could get replenished. So once the raw material goes to a reducing state, an alarm must be sent, and the process being completed, the machine there. So there's so many analytics which need to be updated. So there's a central dashboard to which everything is connected. So that's the IoT in industries. And a connection of all this is the smart city. So the smart city is the idea of the future, wherein everything is just connected in a single button press. So you have the transport system, which is centrally connected. You have the water system that's centrally connected, the energy system is centrally connected, and the medical system that is centrally connected, and all these systems which are together connected. So that is the concept of smart city, the lighting system. It just goes on and on and on. So this is the future. Okay, and the most important area where IoT is used today is in retail. So the moment you enter a mall, okay, out of 10 messages that you receive, at least 6 to 7 will be an offer. Right, so everything is customized. So every detail, every information is collected. Everything is created as a dashboard. So here there are so many things which are all interconnected. Now, why I wanted to tell you all these things is, see, this is what is going to be the future. IoT is going to be the future. Even post-COVID, the contact tracing, the tracing between people, it cannot be done manually. It's not a good method. So contact tracing and the disinfection process. So for everything, what is essential is how close the person has been. So transmitting and receiving, the wireless transmission is very important everywhere. So for every gadget, there is a need for a wireless device. There is a need for a transceiver. There is a need for an antenna. So this is the magnitude where antenna is needed. So there is a mass manufacturing that is essential, that is already happening, and in the future it's going to happen more and more. So that is about IoT. Okay, and I'll just give a small introduction because I just wanted to tell about wearable tags. I thought it would be apt to tell about beacons. So beacons actually are extremely highly deployed, and now for COVID contact tracing also it is going to be used. It's a simple device which transmits its identity. Okay, so this is a beacon that has been disintegrated. So it has an antenna which operates at 2.4 gigahertz, Bluetooth low energy, and it has a battery and a low level software which is the firmware, and Bluetooth smart connectivity module, a computer, an ARM computer, and a casing, silicone casing. So this is about a beacon, right? So what do these beacons do? So just this might seem a little disintegrated, but I'll just tell you how it will get applied. So these beacons, they continuously blink. They simply transmit its identity saying, hi, I'm there. This is my identity. So that's what it does, right? So it frequently transmits its identity, right? And any device that receives it, right, based on the received signal strength indicator, there is a value called RSSI. Based on that, the information it passes to the cloud, various details about the person who's carrying the mobile phone can be obtained, and several processes can be done based on this, right? So yes, I wanted to tell about RSSI, received signal strength indicator. It is nothing but the signal strength that is received by a particular device, say a mobile phone, from a beacon, right? So generally there's a value called measured power, which is the RSSI of that particular beacon at 1 meter distance. So this measured power minus the actual RSSI divided by this 10 quantity into 10, which is the environmental factor. So that will give you the distance of the person from the beacon. So this is very much useful for location tracking, right? So yes, this is what I wanted to say. So we had seen about beacons. So when the device is placed in a particular location, say in a hall, in the wall, it's called a beacon. But when the same device is carried by a person, it's called a tag, right? A wearable tag, like an identity card. So this is a BLE beacon, a tag that's carried by a person, and this is the receiver, which is the gateway, right? So okay, this receiver is placed in this part of the room, and when the person is simply passing through the room, this is the kind of the RSSI pattern. Only near the door there is a high in the pattern. And now when this person is entering the room, firstly there's an increasing trend in the RSSI pattern, and when the person is leaving the room, there is a decreasing trend in the RSSI pattern, right? So yes, now so this is about, just keep in mind, it's used to estimate the entry and exit events of people. Okay, so this is the wristband. There are different kinds of tags, but typically for contact tracing kind of applications, wristband tags and the typical ID card kind of a tag are the ones that are used these days. So these wristbands are tied, and they used to locate people in real time in a particular area, And there are additional options. There is an LED, there is an alarm, there is a button. So when the person say he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller, there's a small storage unit. So everything is a part of this wristband tag. And following that is the card tag. So this is just like the identity card which people wear. So it's just worn by everybody, right? And there is an LED, and there is also an optional button. So it has the RFID firstly. So RFID is for automated check-in. So using the specific identity of the person, any employee can step in using the RFID. Secondly, there is also the BLE. There is the Wi-Fi. So there are different kinds of presses that can be programmed: a single press, a double press, a long press kind of things. So each press can be programmed in a different way. Say, for example, a double press will when a patient is wearing this particular tag and he's making a double press, the information will immediately go to the nurse, and it could alert for an emergency situation, and she will come for a rescue. So this is the kind of application a card tag has. So I'll just present a simple kind of a use case workflow, which will probably help you identify, understand the process a little more. And I think with this, I think since the time is also running, we can just wrap up. So firstly, as I had said, this is the beacon. This is the proximity beacon, which is there on the wall, and it's transmitting the beacons. It's transmitting the packets. So typically, it transmits Eddystone and iBeacon packets at constant intervals with a certain strength, right? So that is the first process that is happening. Now, a person who's wearing this particular wearable tag, okay, what happens? He receives this information. He receives this particular information, and the person, after completing his shift, he's pressing the button, which indicates the completion of a shift, say a long press or a single press or a double press. It can be programmed accordingly. Now, what happens is this particular wearable device will be made in a little advanced way, right? It will be able to store the information of the beacon from where it is received. Say the beacon is in the conference room, so it will be able to store the information that this person is in conference room and he has completed his shift, right? Now everything goes to the cloud. Okay, so now when he presses the button, immediately the information goes to the cloud that this person has completed his shift and he is in this particular place, right? So the cloud could be a public MQTT cloud or a private server. Okay, so every processing happens in the cloud, as in, okay, so it's just a simple information in terms of bits and bytes that goes to the cloud, but it's the cloud which does all the processing. It interacts with various other servers. It interacts with the separate server system. Okay, so it's from this particular place, it's this particular person. Okay, so to whom the next message has to be sent. So everything will be there on the central dashboard. So the cloud will extract all the information. It will make all the processing, and immediately it will send out an alarm to the next person who's in line to take over the shift. So the person who's next in line will receive an alarm. So optionally, a text message also can be sent to the person who has to go and take over the shift, right? So he'll be sent like, this person A has completed his shift, so you need to go to conference room X to take over the shift. So this is the process for this particular use case. So several other simple things like hospitality, you can just call a person to get something you want, to do a particular servicing. Various other operations can be done, and especially in COVID, post-COVID scenarios. So we are all very comfortably placed in a situation wherein we can afford to work from home, but there are not now, even before, right? There are people who cannot afford to work from home. They have to return back to work whatsoever. There are food processing industries, there are pharmaceutical industries, there are emergency services wherein people have to return back to work, wherein the people, the employees are the asset. So how do we protect those people? So contact tracing using this particular technology is very, very much evolving. So as you can see, a particular wearable device, so wearable antennas are used in this particular device. So the wearable antenna, it needs to have an RFID for access control, and it needs to have this Bluetooth low energy 2.4 gigahertz Bluetooth frequency, a Wi-Fi, and then it needs, suppose the person is infected and he's sitting at home, with a button press he has to give the information to the person who's sitting in the company and the server. Then there's a need for an LTE connectivity, so there's a need for an LTE antenna. So there are at least 4 to 5 antennas. GPS for tracking, there are 4 to 5 antennas, and all the antennas cannot be used all the time, right? So it has to be reconfigured, because if everything is used all the time, energy consumption, battery replacement, everything will become an issue. So which is why the design is very crucial. So miniaturization, size reduction is extremely crucial. So just imagine the volume. If every person in a particular company and every such company is using this particular device, then energy consumption is so important. It is so crucial. So which is why wearable antennas, reconfigurable antennas, and several other antennas even, they play a very crucial role, especially with IoT evolving. So yes, that was about my presentation. Just to give you a brief summary, firstly, we had seen about the wearable antennas, its design, and how it works under different situations, like on body, in bent situations, under crumpled situations, with wetness, and about the specific absorption rate. Following that, we saw about the reconfigurable antennas and the different methods with which we could achieve reconfiguration, and the classification of reconfigurable antennas and reconfigurable antennas in cognitive radio. And then we saw about IoT and how important are antennas, wearable antennas and other antennas in IoT, and we just saw a simple flow system. And since I think we are running short of time, I think I'll just complete with this. Thank you so much. Hello.
Hello, ma'am.
Yes.
Ma'am, presentation is not there.
Yeah, 1 second.
Okay, ma'am.
Okay, can you see?
Yes, ma'am.
Yes.
The slideshow, ma'am, slideshow.
Yeah. Yes. Hello.
Hello, ma'am.
Yes.
Hello?
Yes, ma'am.
Madam, I think Madam has completed and we can start the questions. Is it okay, ma'am?
Yes, sir.
Yeah, sir, we will be presenting now. Thank you, ma'am, for a very informative session. So we'll be sharing the questions now.
Yeah.
Ma'am, the first question is from Dr. Sudhakar Rao.
Yes.
Is it visible? The questions are visible?
Yes.
Okay.
Yeah. Yes, are you working in any industry on these things in India? Also, there are significant applications of RFID, and is there work done in India in this area? Yes, actually, I am working in a company called Invikara. So it's into building digital twin of a building, say for an airport, the digital twin. So they are getting into implementing even the RFID aspects also. Yes, significant applications of RFID are definitely there. Even for access control and things like that. So yes, there is work that is being done in India also. There are manufacturers of beacons with RFID. Yes, so that is about the answer for his question. Bending has effect on the polarization and radiation pattern of wearable antenna, how is it quantified? Yes, yes, definitely bending has an effect on the polarization and radiation pattern. However, it has a major role to play with the fabrication. So it's important how durable we are fabricating. If we are using machine-based fabrication methods, then we can design a wearable antenna which is as good as a rigid, a normal antenna. So even so, if an antenna is built in a proper way, even when it is bent, there will not be much of a change. Probably there could be a few nulls. So it's for us to see if it would drastically affect our performance. But however, as far as I have seen, if the antenna is manufactured in a very proper, authentic way, there should not be much of a problem. And yes, is there any design of wearable antenna of 5G application in design perspective? How the effect of earth, ground, and environment on body-centric communication in the gigahertz band is addressed? Yes, there is wearable antenna for 5G applications also, and the effect of earth, ground, and environment on body-centric communications. Well, yes. So as far as the antenna is designed, so it is more than the effect of all these. It is the human body. The antenna is placed in close proximity to the human body, right? So it's the high dielectric constant of the human body which has a major effect on the antenna. So if that is addressed, if we are using structures like electromagnetic band gap structures and AMCs, then I think that itself will take care. There will not be much effect of the other parameters, environmental when the person say he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller, there's a small storage unit, so everything is a part of this. Yes, but pin diode, because of the specific intrinsic region, this is just like pin identity card, which people wear for higher frequency applications by everybody. And it is also there is an LED, evidently, and there is also an optional button. So it has the RFID. It's very evidently proven. RFID is for automated check-in. So RF applications. Using the that is the reason why we are going in for any employee can step in using the SAR will be estimated. Secondly, there is also the BLE, emanated wave from Wi-Fi. So there are different kinds of presses that can be programmed. The simulation, double press, the long simulation of SAR can be performed. Each press can be programmed in a different way. Say for example, a double press which will when a patient is wearing this particular tag and he's what is the role of reconfigurability? The information will immediately go to the nurse, and it will alert for an emergency situation, and she will come for a rescue. There are many. This is the kind of frequencies which are required in wearable applications, starting from GPS to kind of a use Wi-Fi workflow to LTE. Probably when there are so many frequencies involved, there is also a requirement for. And I think with this, since the time is also so reconfigurability plays an important role in wearable antennas. As I had said, this is the beacon. Is there a need to measure dielectric constant of textile every time and it's transmitting before the beacons designing, or can I use typical values? It's always typically it's better to make Eddystone and iBeacon packets a measurement because constant intervals with a certain strength, right? So that is change from fabric to fabric. That is the same jean fabric which you get at a particular shop will have a slightly different value, a different thickness, a different he receives from the one you get in another shop. So it's always better to make a measurement before every design. He's pressing the button, which indicates the completion of a any standard wearable antenna or a single press or a double press. It can be programmed accordingly for user as a what reference. Happens is this particular company does not manufacture wearable antennas. I have actually done advanced research on wearable antennas, and I'm currently working in an IoT-based industry. From where it is received, we don't manufacture wearable antennas. So it will be able to store the information that this person is in conference room and he has completed his shift. Right now, everything goes. Any other questions? Okay. So now no when he presses the button, immediately the information goes to the cloud. Yes, this person has completed his shift and he is in this particular place. Right. So the cloud could be a public MQTT cloud or a private server. Okay, so every
Hello.
processing happens
Sir,
before,
good
as in,
afternoon, sir.
okay, so
Can
it's
you-
just a
can you
simple
hear me?
information yes, sir, in terms of bits
Okay.
and bytes gets
Madam,
goes to the cloud, but it's
madam,
the cloud which does all
Yes,
the
sir.
processing. It
Madam,
interacts with
Rahul, sir.
various other servers.
Madam
It
Rahul, that
interacts
is
with
our
the
most
separate service
respected
system.
Rahul, sir.
Okay, so it's from this particular place. It's this particular
Has
person.
seen your
So
biodata,
to
ma'am.
whom
That
the
is
next
a
message
resume,
has to be
and
sent.
sir
So
was so
everything will be
impressed
there on the central
and tell
dashboard.
good
So the
words
cloud
about
will
you.
extract
So
all
that's
the
what,
information.
Thank you so
It
much,
will
sir.
make all
Thank you.
the
I'm
processing,
humbled
and
and
immediately it will send
sir
out
will
an
help you.
alarm to the next
Sir
person
will
who
help
is
you.
in line to take over the shift.
I,
So the
I,
person
I'm
who is
very
next in
happy
line
that
will receive an
that
alarm.
Sangeeta
So
Velan is very
optionally, a
fortunate
text message also
that
can be
the
sent to the person
top
who has to
person
go and take over the
IEEE
shift, right? So
fellow is
he'll
hearing
be
your lecture,
sent like
Dr.
this person,
Sudhakar Rao.
person A has
That's a
completed his
gift.
shift, so you
And
need
I
to go
told
to
Dr.
conference
Sudhakar
room
Rao one thing, new
X
thing
to
what he did not
take
know.
over the shift. So
That
this is
Dr.
the
S.K.
process
Ramesh was
for
my
this
student
particular
in
use case. So
76
several other
in a different way.
simple things like
Similarly,
hospitality.
I
You
want
can
to
just
tell
call a
Sangeeta
person
Velan,
to
your guide was my
get
student.
something you want to do a particular service, and various other operations
I
can be
think
done,
if I
and
say
especially
Malati was your guide,
in COVID, post-COVID
Definitely, yes, sir.
scenarios.
She's my
So we are all
alma mater.
very
Oh,
comfortably
My
placed
that should
in a
not make
situation
everyone
wherein
think
we
that I am
can
very, very
afford to
old.
work from home, but
But
there are not
proudly
now,
telling
even before,
Dr.
right?
Sudhakar
you are
Rao,
young,
There
sir.
are people
because
who
tomorrow
cannot
we'll
afford to
get
work from
something
home. They
news
have
about
to
Dr.
return
S.K.
back to
Ramesh.
work
But I am
whatsoever.
very proud.
There are food processing
And
industries, there are
Dr.
pharmaceutical
Sangeeta should tell
industries, there are
everyone,
emergency services
Dr.
wherein
Sudhakar
people
Rao
have to
heard your talk.
return back to work,
Yes, sir.
wherein the employees
Maximum
are the asset.
certificate you
So
can get.
how do we
It's a rare
choose those
opportunity.
people? So
No, I
contact
learned
tracing
something today.
using
I
this
think
particular
very good
technology
talk.
is very
Only thing,
very
part
much
of your
important.
lecture
So
I didn't hear
as you
because
can see, a
I went
particular
to some other
wearable device.
PhD
So
student.
wearable antennas are used
Okay,
in this
sir.
particular
Anyway,
device. So
very
the
happy
wearable
to
antenna,
see
it needs to have an
you as well
RFID
as
Thank you so
for
much, sir.
great
access
person
Thank you.
control,
hearing your
and
lecture.
it needs to have this Bluetooth low
Thanks to
energy
Yes,
all.
sir.
F1
Thanks
Yes,
to
gigahertz
sir.
all.
Bluetooth frequency,
I'm humbled.
Wi-Fi, and then it
Thank you
needs,
so much, sir.
suppose
Thank
the
you
person
to
is infected
Sudhakar Rao
and he's
sir,
sitting at
Raghavan
home
sir,
with a button
Perumal Shankar
pressed, and
sirs.
it's really
I'm
give the
humbled.
information to the person who's
Thank you
sitting
so
in the
much, sir.
company and the
You please
server.
tell your
Then
friend Esther.
there's a need for an
Esther's
LTE
biodata,
connectivity, so there's a need for an LTE
Dr.
antenna.
Sudhakar
So
Rao
there
should
are
know.
at least
You
4 to
please
5
send Esther's
antennas. Yes,
biodata
GPS for
to
tracking. There are 4 to
Professor
5 antennas, and
because
all the
as
antennas
Dr.
cannot be used
Sudhakar
all the
ended,
time, right? So
Indians
it
are
has to be
not second
reconfigured,
to
because if
none.
everything is used all the time, energy
Very recently
consumption,
only I
battery
saw
replacement,
Dr.
everything will become an
Esther's
issue. So
biodata.
which is
Really,
why
I
the design is very
Okay.
crucial. So
know
miniaturization, size
Yes, sir.
reduction is extremely crucial. So just imagine the volume. If every person in a particular company and every such company is using this particular device, then energy consumption is so important. It is so crucial. So which is why wearable antennas, reconfigurable antennas, and several other antennas even, they play a very crucial role, especially with IoT evolving. So yes, that was about my presentation. Just to give you a brief summary. Firstly, we had seen about the wearable antennas, its design, and how it works under different situations, like on body, in bent situations, under crumpled situations, with wetness, and about the specific absorption rate. Following that, we saw about the
Excuse me,
reconfigurable
Raghavan
antennas and the
sir.
different
great
methods
So there's
with which
some
we could achieve
disturbance in the
reconfiguration, and the
audio.
classification of reconfigurable antennas and
Audio is not
reconfigurable
clear,
antennas
sir.
in cognitive radio. And then we saw
can
about
request
IoT and
Dr.
how important are antennas, wearable antennas, and other antennas in IoT. And we just
Yeah,
saw
I
a
think
simple flow system.
audio is not
And
working
since I
properly.
think we are running
Yeah,
short of time,
but
I think
very good
I'll just
talk and very
complete with this.
interesting.
Thank
Keep
you.
up
Thank you so
good
much.
work.
Thank you, sir. Thank you. Thank you. I'm so very happy to hear such words from such a great stalwart. Thank you, sir.
Hello, ma'am.
Very
Yes,
good.
yes. Thank
Thank
you,
you.
sir. Thank you. Thank you so much. Yes.
So with this,
presentation is not there.
we are winding up the
Yeah,
session.
1 second.
So the next
Okay, ma'am.
session is scheduled at 1:30 p.m. Thank you, madam, for a very informative
Thank
session.
you. Thank you. Thank you so much, ma'am. Thank you. Okay, can you see?
Yes, ma'am.
Yes.
The slideshow, ma'am, slideshow.
Yeah. Yeah. Yes. Hello?
Hello, ma'am.
Yes, yes,
Hello?
yes, ma'am. Yes, ma'am.
Madam, I think Madam has completed and we can start the questions. Is it okay, ma'am?
Yes, yes,
Yes.
yes, sir. Yes, sir. Yes, sir.
Yeah,
We
yeah.
can.
Sir, we will be presenting now. Thank you, ma'am, for a very informative session. So we'll be
Thank
sharing
you.
the questions now.
Yeah.
Ma'am, the first question is from Dr. Sudhagar Rao.
Yes. Yes.
Is it visible? The questions are
Yes.
visible?
Yes. 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 Yes.
Okay.
Yeah. Yes, are you working in any industry on these things in India? Also, there are significant applications of RFID, and is there work done in India in this area? Yes, actually, I am working in a company called Invicara. So it's into building digital twin of a building, say for an airport, the digital twin. So they are getting into implementing even the RFID aspects also. Yes, yes, significant applications of RFID are definitely there. Even for access control and things like that. So yes, there is work that is being done in India also. There are manufacturers of beacons with RFID. Yes, so that is about the answer for his question. Bending has effect on the polarization and radiation pattern of wearable antenna. How is it quantified? Yes, yes, definitely. Bending has an effect on the polarization and radiation pattern. However, it has a major role to play with the fabrication. So it's important how durable we are fabricating. If we are using machine-based fabrication methods, then we can design a wearable antenna which is as good as a rigid, a normal antenna. So even so, if an antenna is built in a proper way, even when it is bent, there will not be much of a change. Probably there could be a few nulls. So it's for us to see if it would drastically affect our performance. But however, as far as I have seen, if the antenna is manufactured in a very proper, authentic way, there should not be much of a problem. And yes, is there any design of wearable antenna of 5G application in design perspective? How the effect of earth, ground, and environment on body-centric communication in the gigahertz band is addressed? Yes, there is wearable antenna for 5G applications also, and the effect of earth, ground, and environment on body-centric communications. Well, yes. So as far as the antenna is designed, so it is more than the effect of all these. It is the human body. The antenna is placed in close proximity to the human body, right? So it's the high dielectric constant of the human body which has a major effect on the antenna. So if that is addressed, if we are using structures like electromagnetic band gap structures and AMCs, then I think that itself will take care. There will not be much effect of the other parameters, environmental parameters. When the person says he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller. There's a small storage unit. So everything is a part of this. Yes, but pin diode, because of the specific intrinsic region, this is just like pin identity card, which is more suitable for higher frequency applications by everybody. And it is also there is an LED, and there is also an optional button. So it has the RFID. It's very evidently proven RFID is for automated check-in. So RF applications. Using the specific that is the reason why we are going in for any employee can step in using the SAR will be estimated. Secondly, there is also the emanated wave from Wi-Fi. So there are different kinds of presses that can be programmed. The simulation, a double press, a long press kind of things can be performed. Each press can be programmed in a different way. Antenna say, for example, a double press which will when a patient is wearing this particular tag and is what is the role of reconfigurability? The information will immediately go to the nurse, and wearable antennas for an emergency situation, and she will come for a rescue. There are many. This is the kind of application frequencies which are required in wearable applications, starting from GPS to Bluetooth kind of a use Wi-Fi workflow, which will probably when there are so many frequencies involved, there is also a requirement for, and I think with this configure from one to the other. So reconfigurability plays an important role in wearable antenna. As I had said, this is the beacon. Is there a need to measure dielectric constant of textile every time before making and transmitting before the beacons designing, or can I use typical values? It's always typically it's better to make Eddystone and iBeacon packets a measurement because constant intervals with a certain strength, right? So that is change from fabric to fabric. That is the same jean fabric which you get at a particular shop will have a slightly different value, a different thickness, a different he receives from the one you get in another shop. So it's always better to make a measurement before every design. He's pressing the button, which indicates the completion of a any standard wearable antenna or a single press or a double press that can be programmed accordingly for user as a reference. This particular company does not manufacture wearable antennas. I have actually done research on wearable antennas, and I'm currently working in an IoT-based industry. From where it is received, we don't manufacture wearable antennas. So it will be able to store the information that this person is in conference room and he has completed his shift. Right now, everything goes. Any other questions? Okay. So now,
no
when
more
he presses
questions,
the button,
Madam,
immediately
Raghavan
the
sir
information
is
goes to the cloud. Yes, this person has completed his shift
Raghavan
and
sir?
he is in this particular place. Right. So the cloud could be a public MQTT cloud or a private server. Okay, so every
Hello?
processing happens in the cloud.
Good
As in,
afternoon, sir.
okay, so
Can
it's
you-
just a
can you
simple
hear me?
information
Yes,
sir, in terms of bits
Okay.
and bytes that
Madam,
goes to the cloud, but it's
madam,
the cloud which does all the processing. It
Madam,
interacts with
Raghavan sir,
various other servers.
Madam
It
Raghavan, that
interacts
is
with
our
the
most
separate server
respected
system.
Raghavan sir.
Okay, so it's from this particular place. It's this particular
Has
person.
seen your
So
biodata,
to
ma'am.
whom
That
the
is
next
a
message
resume,
has to
and
be
the
sent.
sir
So
was so
everything will be
impressed
there on the central
and tell
dashboard.
good
So the
words
cloud
about
will
you.
extract
So
all
that's
the
what,
information.
thank you
So much, it will make all the
I'm
processing,
humbled
and immediately it will send
Sir
out
will
an
conclude.
alarm to the next person
Okay.
who's in line to take over the shift. So the person
I'm
who's
very
next in
happy
line
that
will receive an
Dr.
alarm.
Sangeeta
So
Velan is very
optionally, a
fortunate
text message
that
also can be
the
sent to the person
top
who has to
person
go and take over the
IEEE
shift, right? So
fellow is
he'll
hearing
be
your lecture,
sent like
Dr.
this person,
Sudhakar Rao.
person A has
That's a
completed his
gift.
shift, so you
And
need to
I
go
told
to
Dr.
conference
Sudhakar Rao
room
one thing, new
X
thing
to
what he did not
take
know.
over the shift. So
That
this is
Dr.
the
S.K.
process
Ramesh was
for
my
this
student
particular
in
use case. So
76
several other
in a different way.
simple things like
Similarly,
hospitality.
I
You
want
can
to tell
just call a
Sangeeta
person
Velan,
to
your guide was my
get
student.
something you want to do a particular service. Various other operations
I
can be
think
done,
if I
and
say
especially
Malati was your guide,
in COVID, post-COVID
yes, sir,
scenarios.
she's my
So we are
alma
all
mater.
very comfortably
that,
placed
that should
in a
not make
situation
everyone
wherein
think
we
that I am
can
very, very
afford to
old.
work from home, but
But
there are not
proudly
now,
telling
even before.
Dr.
Right?
Sudhakar Rao,
There are people
because
who
tomorrow
cannot
we'll
afford to
get
work from home.
something
They
news
have
about
to
Dr.
return
S.K.
back to
Ramesh,
work
but I am
whatsoever.
very proud.
There are food processing
And
industries, there are
Dr.
pharmaceutical
Sangeeta should tell
industries, there are
everyone,
emergency services
Dr.
wherein
Sudhakar
people
Rao
have to
heard your talk.
return back to work.
That is a
Wherein the people, the employees
maximum
are the asset.
certificate you
So
can get.
how do we
It's a rare
choose those
opportunity.
people? So
No, I
contact
learned
tracing
something today.
using
I think
this particular
very good
technology
talk.
is very
Only thing,
very
part
much
of your
evolving.
lecture
So
I didn't hear
as you
because
can see, a
I went to
particular
some other
wearable device.
PhD
So
student.
wearable antennas are used in this particular
Anyway,
device. So
very
the
happy
wearable
to
antenna,
see
it needs to have an
you as well
RFID
as
for
great
access
person
control,
hearing your
and
lecture.
it needs to have this Bluetooth low
Thanks
energy
to all.
2.4
Thanks to
gigahertz
all.
Bluetooth frequency,
I'm humbled.
Wi-Fi, and then
Thank you so much, sir.
suppose
Thank
the
you
person
to
is infected
Sudhakar Rao
and he's
sir,
sitting at
Raghavan
home
sir,
with a button
Perumal Shankar
press,
sir,
and it's really give
I'm
the information to
humbled.
the person who's sitting
so
in the
much.
company and the
You please
server.
tell your
Then
friend Esther.
there's a need for an
Esther's
LTE
biodata,
connectivity, so there's a need for an LTE
Dr.
antenna.
Sudhakar
So
Rao
there
should
are
know.
at least 4
You
to
please
5
send Esther's
antennas. Yes,
biodata
GPS for
to
tracking. There are 4 to
Professor
5 antennas, and
because
all the
as
antennas
Dr.
cannot be used
Sudhakar
all the
ended,
time, right? So
Indians
it
are
has to be
not second
reconfigured,
to
because if
none.
everything is used all the time, energy
Very recently
consumption,
only I
battery
saw
replacement,
Dr.
everything will become an
Esther's
issue. So
biodata.
which is
Really,
why the design is very crucial. So miniaturization, size reduction is extremely crucial. So just imagine the volume. If every person in a particular company and every such company is using this particular device, then energy consumption is so important. It is so crucial. So which is why wearable antennas, reconfigurable antennas, and several other antennas even, they play a very crucial role, especially with IoT evolving. So yes, that was about my presentation. Just to give you a brief summary. Firstly, we have seen about the wearable antennas, its design, and how it works under different situations, like on body, in bent situations, under crumpled situations, with wetness, and about the specific absorption rate. Following that, we saw about the reconfigurable antennas and the different methods with which we could achieve reconfiguration, and the classification of reconfigurable antennas and reconfigurable antennas in cognitive radio. And then we saw about IoT and how important are antennas, wearable antennas, and other antennas in IoT. And we just saw a simple flow system
is not
And
working
since I
properly.
think we are running
Yeah,
short of time,
but
I think
very good
I'll
talk
just
and very
complete with this.
interesting.
Thank
Keep
you.
up
Thank you so
good
much.
work.
Thank you, sir. Thank you. Thank you. I'm so very happy
Hello?
to hear such words from such a great stalwart. Thank you, sir.
Hello, ma'am.
Very
Yes,
good.
yes. Thank
Thank
you,
you.
sir. Thank you. Thank you so much. Yes.
Ma'am,
So with
presentation
this,
is not there.
we are winding up the
Yeah,
session.
1 second.
So the
Okay,
next
ma'am.
session is scheduled at 1:30 p.m. Thank you, madam, for a very informative
Thank
session.
you. Thank you. Thank you so much, ma'am. Thank you. Okay, can you see?
Yes, ma'am.
Yes.
The slideshow, ma'am. Slideshow.
Yeah. Yeah. Yes. Hello?
Hello, ma'am.
Yes,
Hello.
ma'am. Yes, ma'am.
Madam, I think Madam has completed and we can start the questions. Is it okay, ma'am?
Yes,
Yes.
sir. Yes, sir.
Yeah,
We
yeah.
can.
Sir, we will be presenting now. Thank you, ma'am, for a very informative session. So we'll be
Thank
sharing
you.
the questions now.
Yeah.
Ma'am, the first question is from Dr. Sudhagar Rao.
Yes.
Is it visible? The questions are
Yes,
visible?
yes.
Okay.
Yeah. Yes, are you working in any industry on these things in India? Also, there are significant applications of RFID, and is there work done in India in this area? Yes, actually, I am working in a company called Invikara. So it's into building digital twin of a building, say for an airport, the digital twin. So they are getting into implementing even the RFID aspects also. Yes, significant applications of RFID are definitely there. Even for access control and things like that. So yes, there is work that is being done in India also. There are manufacturers of beacons with RFID. Yes, so that is about the answer for his question. Bending has effect on the polarization and radiation pattern of wearable antenna. How is it quantified? Yes, definitely. Bending has an effect on the polarization and radiation pattern. However, it has a major role to play with the fabrication. So it's important how durable we are fabricating. If we are using machine-based fabrication methods, then we can design a wearable antenna which is as good as a rigid, a normal antenna. So if an antenna is built in a proper way, even when it is bent, there will not be much of a change. Probably there could be a few nulls. So it's for us to see if it would drastically affect our performance. But however, as far as I have seen, if the antenna is manufactured in a very proper, authentic way, there should not be much of a problem. And yes, is there any design of wearable antenna of 5G application in design perspective? How the effect of earth, ground, and environment on body-centric communication in the gigahertz band is addressed? Yes, there is wearable antenna for 5G applications also, and the effect of earth, ground, and environment on body-centric communications. Well, yes. So as far as the antenna is designed. So it is more than the effect of all these. It is the human body. The antenna is placed in close proximity to the human body, right? So it's the high dielectric constant of the human body which has a major effect on the antenna. So if that is addressed, if we are using in real time in a particular area structures and AMCs, then I think that itself will take care. There will not be much effect of the other parameters, environmental when the person says he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller, there's a small storage unit, so everything is a part of this. Yes, but pin diode, because of the specific intrinsic region, this is just like the identity card, which more suitable for higher frequency applications by everybody. And it is also there is an LED, evidently there is also an optional button. So it has the RFID. It's very evidently proven. RFID is for automated check-in. So RF applications. Using the that is the reason why we are going in for any employee can step in using the RFID. Will be estimated. Secondly, there is also the emanated wave from Wi-Fi. So there are different kinds of presses that can be programmed. The simulation, double press, the long simulation of SAR can be performed. Each press can be programmed in a different way. Antenna say, for example, a double press which will when a patient is wearing this particular and what is the role of reconfigurability? The information will immediately go to the nurse, and it will alert for an emergency situation, and she will come for a rescue. There are many. This is the kind of frequencies which are required in wearable applications, starting from GPS to kind of a use case workflow to LTE. Probably when there are so many frequencies involved, there is also a requirement for. I think with this configure from the time is also so reconfigurability plays an important role in wearable antennas. As I had said, this is the is there a need to measure dielectric constant of textile every time and it's transmitting for the beacons designing, or can I use typical values? So it's always typically it's better to make Eddystone and iBeacon packets a measurement because constant intervals with a certain strength, right? So that is change from fabric to fabric that is the same jean fabric which you get at a particular shop will have a slightly different value, a different thickness, a different he receives from the one you get in another shop. So it's always better to make a measurement before every design. He is pressing the button, which indicates the completion of any standard wearable antenna or a single press or a double press. It can be programmed accordingly. For user as a what happens is this particular company does not manufacture wearable antennas. I have actually done advanced research on wearable antennas, and I'm currently working in an IoT based industry. From where it is received, we don't manufacture wearable antennas. So it will be able to store the information that this person is in conference room and he has completed his shift. Right now, everything goes. Any other questions? Okay. So now no when he presses the button, immediately the information goes to the cloud. Yes, this person has completed his shift and he is in this particular place. Right. So the cloud could be a public MQTT cloud or a private server. Okay, so every processing happens.
Good afternoon, sir.
Okay, so it's just a simple information in terms of bits and bytes which goes to the cloud, but it's the cloud which does all the processing. It interacts with various other servers. It interacts with the separate server system. Okay, so it's from this particular place. This particular
has seen your biodata, that is a resume, and sir was so impressed
there on the central dashboard.
So
the cloud will extract all the information. Thank you so much, sir. Thank you. I'm humbled, and it will send out an alarm to the next person who is in line to take over the shift. So the person who is next in line will receive an alarm. So optionally, a text message also can be sent to the person who has to go and take over the shift, right? So he'll be sent like this person A has completed his shift, so you need to go to conference room X to take over the shift. So this is the process for this particular use case. So several other simple things like hospitality.
I want to tell Sangeeta Velan, your guide was my student.
Get something you want to do a particular service. Various other operations.
I think if I say Malati was your guide,
in COVID, post-COVID scenarios, so we are all very comfortably placed in a situation wherein we can afford to work from home. But there are not now, even before. There are people who cannot afford to work from home. They have to return back to work whatsoever.
But I'm very proud.
There are food processing industries. There are pharmaceutical industries. There are emergency services wherein people have to return back to work. Yes, the people, the employees.
Certificate you can get.
How do we protect those people? So
No, I
contact
learned
tracing
something today.
using
I think,
this particular
very good
technology
talk.
is very
Only thing,
very
part
much
of your
important.
lecture
So
I didn't hear
as you
because
can see, a
I went
particular
to some other
wearable device.
PhD
So
student.
wearable antennas are used in this
Anyway,
particular device. So
very
the
happy
wearable
to
antenna,
see
it needs to have an
you as well
RFID
as
for
a great
access
person
control,
sharing your
and
lecture.
it needs to have this Bluetooth low
Thanks
energy
to
as
all.
control
Thanks to
regarding
all.
Bluetooth frequency,
I'm humbled.
Wi-Fi, and then
Thank you so much, sir.
suppose
Thank
the
you
person
to
is infected
Sudhakar Rao
and he's
sir,
sitting at
Raghavan
home
sir,
with a button
Perumal Shankar
pressed,
sir,
and
to
it's really give
I'm
the information to
humbled.
the person who's
Thank you
sitting
so
in the
much, sir.
company and the
You please
server.
tell your
Then
friend Esther.
there's a need for an
Esther's
LTE
biodata.
connectivity, so there's a need for an LTE
Dr.
antenna.
Sudhakar
So
Rao
there
should
are
know.
at least
You
4 to
please
5
send Esther's
antennas. Yes,
biodata
GPS for
to
tracking. There are 4 to
Professor
5 antennas, and
because
all the
as
antennas
Dr.
cannot be used
Sudhakar
all the
ended,
time, right? So
Indians
it
are
has to be
not second
reconfigured,
to
because if
none.
everything is used all the time, energy
Very recently
consumption,
only I
battery
saw
replacement,
Dr.
everything will become an
Esther's
issue. So
biodata.
which is
Really,
why the design is very
Okay.
crucial. So
know,
miniaturization, size
Yes, sir.
reduction is extremely crucial. So just imagine the volume. If every person in a particular company and every such company is using this particular device, then energy consumption is so important. It is so crucial. So which is why wearable antennas, reconfigurable antennas, and several other antennas even, they play a very crucial role, especially with IoT evolving. So yes, that was about my presentation. Just to give you a brief summary. Firstly, we have seen about the wearable antennas, its design, and how it works under different situations, like on body, in bent situations, under crumpled situations, with wetness, and about the specific absorption rate. Following that, we saw about the
Excuse me,
reconfigurable
Raghavan
antennas and the
sir.
different
great
methods
So there's
with which
some
we could achieve
disturbance in the
reconfiguration, and the
audio.
classification of reconfigurable antennas and
Audio is not
reconfigurable antennas
clear,
in
sir.
in cognitive radio. And then we saw about IoT and how important are antennas, wearable antennas, and other antennas in IoT. And we just
Yeah,
saw
I
a
think
simple flow system.
audio is not
And
working
since I
properly.
think we are running
Yeah,
short of
but
time, I think
very good
I'll just
talk and very
complete with this.
interesting.
Thank
Keep
you.
up
Thank you so
good
much.
work.
Thank you, sir. Thank you. Thank you. I'm so very happy to hear such words from such a great stalwart. Thank you, sir.
Hello, ma'am.
Very
Yes,
good.
yes. Thank
Thank
you,
you.
sir. Thank you. Thank you so much. Yes.
So with this,
presentation is not there.
we are winding up the
Yeah,
session.
1 second.
So the next
Okay, ma'am.
session is scheduled at 1:30 p.m. Thank you, madam, for a very informative session.
Thank you. Thank you. Thank you so much, ma'am. Thank you. Okay, can you see?
Yes, ma'am.
Yes.
The slideshow, ma'am.
Yeah,
Slideshow.
yeah. Yeah. Yes. Hello?
Hello, ma'am.
Yes,
Hello?
yes, ma'am. Yes, ma'am.
Madam, I think Madam has completed and we can start the questions. Is it okay, ma'am?
Yes,
Yes.
sir.
Yeah,
we
yeah.
can.
Sir, we will be presenting now. Thank you, ma'am, for a very informative session. So we'll be
Thank
sharing
you.
the questions now.
Yeah.
Ma'am, the first question is from Dr. Sudhakar Rao.
Yeah.
Is it visible? The questions are
Yes,
visible?
yes.
Okay.
Yeah. Yes, are you working in any industry on these things in India? Also, there are significant applications of RFID, and is there work done in India in this area? Yes, actually, I am working in a company called Invicara. So it's into building digital twin of a building, say for an airport, the digital twin. So they are getting into implementing even the RFID aspects also. Yes, yes, significant applications of RFID are definitely there. Even for access control and things like that. So yes, there is work that is being done in India also. There are manufacturers of beacons with RFID. Yes, so that is about the answer for his question. Bending has effect on the polarization and radiation pattern of wearable antenna. How is it quantified? Yes, yes, definitely. Bending has an effect on the polarization and radiation pattern. However, it has a major role to play with the fabrication. So it's important how durable we are fabricating. If we are using machine-based fabrication methods, then we can design a wearable antenna which is as good as a rigid, a normal antenna. So even so, if an antenna is built in a proper way, even when it is bent, there will not be much of a change. Probably there could be a few nulls. So it's for us to see if it would drastically affect our performance. But however, as far as I have seen, if the antenna is manufactured in a very proper, authentic way, there should not be much of a problem. And yes, is there any design of wearable antenna of 5G application in design perspective? How the effect of earth, ground, and environment on body-centric communication in the gigahertz band is addressed? Yes, there is wearable antenna for 5G applications also, and the effect of earth, ground, and environment on body-centric communications. Well, yes. So as far as the antenna is designed, so it is more than the effect of all these. It is the human body. The antenna is placed in close proximity to the human body, right? So it's the high dielectric constant of the human body which has a major effect on the antenna. So if that is addressed, if we are using structures like electromagnetic band gap structures and AMCs, then I think that itself will take care. There will not be much effect of the other parameters, environmental parameters. When the person says he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller. There's a small storage unit. So everything is a part of this. Yes, but pin diode, because of the specific intrinsic region, this is just like pin identity card, which more suitable for higher frequency applications by everybody. And it is also there is an LED, evidently there is also an optional button. So it has the RFID. It's very evidently proven. RFID is for automated check-in. So RF using the that is the reason why we are going in for any employee can step in using the SAR will be estimated. Secondly, there is also the emanated wave from Wi-Fi. So there are different kinds of presses that can be programmed. The simulation, double press, the long press of SAR can be performed. Each press can be programmed in a different way. Say for example, a double press which will when a patient is wearing this particular and what is the role of reconfigurability? The information will immediately go to the nurse, and wearable antenna for an emergency situation, and she will come for a rescue. There are many. This is the kind of frequencies which are required in wearable applications, starting from GPS to Bluetooth kind of a use case workflow, LTE. Probably when there are so many frequencies involved, there is also a requirement for. And I think with this configure from one to the other. So reconfigurability plays an important role in wearable antennas. As I had said, this is the is there a need to measure dielectric constant of textile every time and it's transmitting before the beacons designing, or can I use typical values? So it's always typically it's better to make Eddystone and iBeacon packets a measurement because constant intervals every certain strength, right? So that is change from fabric to fabric. That is the same jean fabric which you get at a particular shop will have a slightly different value, a different thickness, a different he receives from the one you get in another shop. So it's always better to make a measurement before every design. He's pressing the button, which indicates the completion of any standard wearable antenna or a single press or a double press that can be programmed accordingly. For user as a reference, this particular wearable does not manufacture wearable antennas. I have actually done research on wearable antennas, and I'm currently working in an IoT-based industry. From where it is received, we don't manufacture wearable antennas. So it will be able to store the information that this person is in conference room and he has completed his shift. Right now, everything goes. Any other questions? Okay. So now
no
when
more
he presses
questions,
the button, immediately the information goes to the cloud. Yes, this person has completed his shift and he is in this particular place. Right. So the cloud could be a public MQTT cloud or a private server. Okay, so every
Hello.
processing happens
Sir,
this way.
good
As in,
afternoon, sir.
okay, so
Can
it's
you-
just a
can you
simple
hear me?
information
Yes, sir.
in
Yes,
terms
sir.
of bits
Okay.
and bytes that
Madam,
goes to the cloud, but it's
madam,
the cloud which does all
Yes,
the
sir.
processing. It
Madam,
interacts with
Raghavan, sir.
various other servers.
Madam
It
Raghavan, that
interacts
is
with
our
the
most
separate service
respected
system.
Raghavan, sir.
Okay, so it's from this particular place. It's this particular
Has
person.
seen your
Okay. So
biodata,
to
ma'am.
whom
That
the
is
next
a
message
resume,
has to
and
be
sir
sent. So
was so
everything will be
impressed
there on the central
and tell
dashboard.
good
So the
words
cloud
about
will
you.
extract
So
all
that's
the
what
information.
Thank you so
It
much,
will
sir.
make all
Thank you.
the
I'm
processing,
humbled
and
and
immediately
sir,
it will send
sir
out
will
an
conclude.
alarm to the next person
Okay.
who's in line to take over the shift.
I,
So the
I,
person
I'm
who's
very
next
happy
in line
that
will receive an
that
alarm.
Sangeeta
So
Velan is very
optionally, a
fortunate
text message
that
also can be
the
sent to the person
top
who has to
person
go and take over the
IEEE
shift, right? So
fellow is
he'll
hearing
be
your lecture,
sent like
Dr.
this person,
Sudhakar Rao.
person A has
That's a
completed his
gift.
shift, so you
And
need
I
to go
told
to
Dr.
conference
Sudhakar Rao
room
one thing, new
X
thing
to
what he did not
take
know.
over the shift. So
That
this is
Dr.
the
S.K.
process
Ramesh was
for
my
this
student
particular
in
use case. So
76
several other
in a different way.
simple things like
Similarly,
hospitality.
I
You
want
can
to tell
just call a
Sangeeta
person
Velan,
to
your guide was my
get
student.
something you want to do a particular service. Various other operations
I
can be
think
done,
if I
and
say
especially
Malati was your guide,
in COVID, post-COVID
Definitely, yes, sir.
scenarios.
She's my
So we
alma
are all
mater.
very
My
comfortably
idol.
placed
that should
in a
not make
situation
everyone
wherein
think
we
that I'm
can
very, very
afford to
old.
work from home. But
But
there are not
proudly
now,
telling
even before.
Dr.
Right?
Sudhakar Rao,
There are people
because
who
tomorrow
cannot
we'll
afford to
get
work from home.
something
They
news
have
about
to
Dr.
return
S.K.
back to
Ramesh,
work
but I'm
whatsoever.
very proud.
There are food processing
And
industries, there are
Dr.
pharmaceutical
Sangeeta should tell
industries, there are
everyone,
emergency services
Dr.
wherein
Sudhakar
people
Rao
have to
heard your talk.
return back to work.
Yes, sir.
Wherein the people, the employees
Maximum
are the asset.
certificate you
So
can get.
how do we
It's a rare
choose those
opportunity.
people? So
No, I
contact
learned
tracing
something today.
using
I think
this particular
very good
technology
talk.
is very
Only thing,
very
part
much
of my
Thank you,
evolving.
lecture
So
I didn't hear
as you
because
can see, a
I went to
particular
some other
wearable device.
PhD
So wearable
student.
antennas are used
Okay,
in this
sir.
particular
Anyway,
device. So
very
the
happy
wearable
to
antenna,
see
it needs to have an
you as well
RFID
as
Thank you so
for
much, sir.
great
accessing
person
Thank
the
hearing your
and
lecture.
it needs to have this Bluetooth low
Thanks to
energy
all.
2.4
Thanks to
gigahertz
all.
Bluetooth frequency,
I'm humbled.
Wi-Fi, and then it
Thank you
needs,
so much, sir.
suppose
Thank
the
you
person
to
is infected
Sudhakar Rao
and he's
sir,
sitting at
Raghavan
home
sir,
with a
Perumal
button
Shankar
pressed,
sir.
and
It's really,
give
I'm
the information to
humbled.
the person who's
Thank you
sitting
so
in the
much, sir.
company and the
You please
server.
tell your
Then
friend Esther.
there's a need for an
Esther's
LTE
biodata,
connectivity, so there's a need for an LTE
Dr.
antenna.
Sudhakar
So
Rao
there
should
are
know.
at least
You
4 to
please
5
send Esther's
antennas. Yes,
biodata
GPS for
to
tracking. There are 4 to
process.
5 antennas, and
Because
all the
as
antennas
Dr.
cannot be used
Sudhakar
all the
ended,
time, right? So
Indians
it has
are
to be
not second
reconfigured,
to
because if
none.
everything is used all the time, energy
Very recently
consumption,
only I
battery
saw
replacement,
Dr.
everything will become an
Esther's
issue. So
biodata.
which is
Really,
why the design is very
Okay.
crucial. So
no,
miniaturization, size
Yes, sir.
reduction is extremely crucial. So just imagine the volume. If every person in a particular company and every such company is using this particular device, then energy consumption is so important. It is so crucial. So which is why wearable antennas, reconfigurable antennas, and several other antennas even, they play a very crucial role, especially with IoT evolving. So yes, that was about my presentation. Just to give you a brief summary. Firstly, we have seen about the wearable antennas, its design, and how it works under different situations, like on body, in bent situations, under crumpled situations, with wetness, and about the specific absorption rate. Following that, we saw about the
Excuse me,
reconfigurable
Raghavan
antennas and the
sir.
different
great
methods
There's
with which
some
we could achieve
disturbance in the
reconfiguration and the
audio.
classification of reconfigurable antennas and
Audio is not
reconfigurable antennas
clear,
in
sir.
in cognitive radio. And then we saw about IoT and how important are antennas, wearable antennas, and other antennas in IoT. And we just
Yeah, I
saw a
think
simple
his
flow system.
audio is not
And
working
since
properly.
I think we are running
Yeah,
short of
but
time, I think
very good
I'll just
talk and very
complete with this.
interesting.
Thank
Keep
you.
up
Thank you so
good
much.
work.
Thank you, sir. Thank you. Thank you. I'm so very happy to hear such words from such a great stalwart. Thank you, sir.
Hello, ma'am.
Very
Yes, yes. Thank
Thank
you,
you.
sir. Thank you. Thank you so much. Yes.
So with this,
Presentation is not there.
we are winding up the session.
Yeah, one second.
So the
Okay,
next
ma'am.
session is scheduled at 1:30 p.m. Thank you, madam, for a very informative session.
Thank you. Thank you. Thank you so much, ma'am. Thank you. Okay, can you see?
Yes, ma'am.
Yes.
The slideshow, ma'am. Slideshow.
Yeah. Yeah. Yes. Hello?
Hello, ma'am.
Yes, yes,
Hello?
yes, ma'am. Yes, ma'am.
Madam, I think Madam has completed and we can start the questions. Is it okay, ma'am?
Yes, yes,
Yes.
yes, sir. Yes, sir. Yes, sir.
Yeah,
we
yeah.
can.
Sir, we will be presenting now. Thank you, ma'am, for a very informative session. So we'll be
Thank
sharing
you.
the questions now.
Yeah.
Ma'am, the first question is from Dr. Sudhagar Rao.
Yes, yes.
Is it visible? The questions are
Yes,
visible?
yes, 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 yes.
Okay.
Yeah. Yes, are you working in any industry on these things in India? Also, there are significant applications of RFID, and is there work done in India in this area? Yes, actually, I am working in a company called Invikara. So it's into building digital twin of a building, say for an airport, the digital twin. So they are getting into implementing even the RFID aspects also. Yes, yes, significant applications of RFID are definitely there. Even for access control and things like that. So yes, there is work that is being done in India also. There are manufacturers of beacons with RFID. Yes, so that is about the answer for his question. Bending has effect on the polarization and radiation pattern of wearable antenna. How is it quantified? Yes, yes, definitely. Bending has an effect on the polarization and radiation pattern. However, it has a major role to play with the fabrication. So it's important how durable we are fabricating. If we are using machine-based fabrication methods, then we can design a wearable antenna which is as good as a rigid, a normal antenna. So even so, if an antenna is built in a proper way, even when it is bent, there will not be much of a change. Probably there could be a few nulls. So it's for us to see if it would drastically affect our performance. But however, as far as I have seen, if the antenna is manufactured in a very proper, authentic way, there should not be much of a problem. And yes, is there any design of wearable antenna of 5G application in design perspective? How the effect of earth, ground, and environment on body-centric communication in the gigahertz band is addressed? Yes, there is wearable antenna for 5G applications also, and the effect of earth, ground, and environment on body-centric communications. Well, yes. So as far as the antenna is designed, so it is more than the effect of all these. It is the human body. The antenna is placed in close proximity to the human body, right? So it's the high dielectric constant of the human body which has a major effect on the antenna. So if that is addressed, if we are using in real time in a particular area structures and AMCs, then I think that itself will take care. There will not be much effect of the other parameters, environmental when parameters, the person says he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller. There's a small storage unit. So everything is a part of this. Yes, but pin diode, because of the specific intrinsic region, this is just like the identity card, which more suitable for higher frequency applications by everybody. And it is also there is an LED, evidently there is also an optional button. So it has the RFID. It's very evidently proven. RFID is for automated check-in. So RF applications. Using the specific, that is the reason why we are going in for any employee can step in using the SAR will be estimated. Secondly, there is also the BLE, emanated wave from Wi-Fi. So there are different kinds of presses that can be programmed. The simulation, double press, the long simulation of SAR can be performed. Each press can be programmed in a different way. Antenna, say for example, a double press which will when a patient is wearing this particular and what is the role of reconfigurability? The information will immediately go to the nurse, and it will alert for an emergency situation, and she will come for a rescue. There are many. This is the kind of frequencies which are required in wearable applications, starting from GPS to kind of a use case workflow to LTE. Probably when there are so many frequencies involved, there is also a requirement for, and I think with this configure from one to the other. So reconfigurability plays an important role in wearable antenna. As I had said, this is the beacon. Is there a need to measure dielectric constant there on the every time and it's transmitting for the beacons designing, or can I use typical values? So it's always typically it's better to make Eddystone and iBeacon packets a measurement because constant intervals every with a certain strength, right? So that is change from fabric to fabric. That is the same jean fabric which you get at a particular shop will have a slightly different value, a different thickness, a different he receives from the one you get in another shop. So it's always better to make a measurement before every design. He's pressing the button, which indicates the completion of a any standard variable press or a single press or a double press. It can be programmed accordingly for user as a reference. This particular company does not manufacture variable antennas. I have actually done research on variable antennas, and I'm currently working in an IoT based industry. From where it is received, we don't manufacture variable antennas. So it will be able to store the information that this person is in conference room and he has completed his shift. Right now, everything goes. Any other questions? Okay. So now
no
when
more
he presses
questions,
the button,
Madam,
immediately the information goes to the cloud. Yes, this person has completed his shift
Raghavan,
and
sir.
he is in this particular place. Right. So the cloud could be a public MQTT cloud or a private server. Okay, so every
Hello.
processing happens.
Sir, good
as in,
afternoon, sir.
okay, so
Can
it's
you-
just a
can you
simple
hear me?
information
Yes,
sir, in terms of bits
Okay.
and bytes that
Madam,
goes to the cloud, but it's
madam.
the cloud which does all the processing. It
Madam,
interacts with
Raghavan, sir.
various other servers.
Madam,
It
Raghavan, that
interacts
is
with
our
the
most
separate server
respected
system.
Raghavan, sir.
Okay, so it's from this particular place. It's this particular
has
person.
seen your
So
biodata,
to
ma'am.
whom
That
the
is
next
a
message
resume,
has to be
and
sent.
sir
So
was so
everything will be
impressed
there on the central
and tell
dashboard.
good
So the
words
cloud
about
will
you.
extract
So
all
that's
the
what
information.
Thank you
It
so
will
much,
make
sir.
all
Thank
the
you.
processing.
humbled
And
and
immediately it will send
Sir
out
will
an
help you.
alarm to the next person
Sir,
who is in line to take over the shift. So the
I
person
am
who is
very
next
happy
in line
that
will receive an
that
alarm.
Sangeeta
So
Velan is very
optionally, a
fortunate
text message
that
also can be
the
sent to the person
top
who has to
person
go and take over the
IEEE
shift, right? So
fellow is
he'll
hearing
be
your lecture,
sent like
Dr.
this person,
Sudhakar Rao.
person A has
That's a
completed his
gift.
shift, so you
And
need
I
to go
told
to
Dr.
conference
Sudhakar Rao
room
one thing, new
X
thing
to
what he did not
take
know.
over the shift. So
That
this is
Dr.
the
S.K.
process
Ramesh was
for
my
this
student
particular
in
use case. So
76
several other
in a different way.
simple things like
Similarly,
hospitality.
I
You
want
can
to tell
just call a
Sangeeta
person
Velan,
to
your guide was my
get
student.
something you want to do a particular service in various other operations
I
can be
think
done,
if I
and
say
especially
Malati was your guide,
in COVID, post-COVID
Yes, sir,
scenarios.
she's my
So we are all very comfortably placed
that should
in a
not make
situation
everyone
wherein
think
we
that I am
can
very, very
afford to
old.
work from home, but
But
there are not
proudly
now,
telling
even before.
Dr.
Right?
Sudhakar
There are people
because
who
tomorrow
cannot
we'll
afford to
get
work from
something
home. They
news
have
about
to
Dr.
return
S.K.
back to
Ramesh,
work
but I am
whatsoever.
very proud.
There are food processing
And
industries, there are
Dr.
pharmaceutical
Sangeeta should tell
industries, there are
everyone,
emergency services
Dr.
wherein
Sudhakar
people
Rao
have to
heard your talk.
return back to work.
That is a
Wherein the people, the employees
maximum
are the asset.
certificate you
So
can get.
how do we
It's a rare
choose those
opportunity.
people? So
No, I
contact
learned
tracing
something today.
using
I think,
this particular
very good.
technology is very
Only thing
very
part
much
of your
important.
lecture
So
I didn't hear
as you
because
can see, a
I went to
particular
some other
variable device.
PhD
So
student.
variable antennas are used in this particular
Anyway,
device. So
very
the
happy
variable
to
antenna,
see
it needs to have an
you as well
RFID
as
for
a great
access
person
control,
hearing your
and
lecture.
it needs to have this Bluetooth low
Thanks
energy
all.
8.4
Thanks
gigahertz
all.
Bluetooth frequency,
I'm humbled.
Wi-Fi, and then
Thank you so much, sir.
suppose
Thank
the
you
person
to
is infected
Sudhakar Rao
and he's
sir,
sitting at
Raghavan
home
sir,
with a button
Perumal
press.
Shankar sir,
He has
and
to
it's really
give
I'm
the information to
humbled.
the person who's
Thank you
sitting
so
in the
much.
company and the
You
server.
please tell your
Then
friend Esther.
there's a need for an
Esther's
LTE
biodata,
connectivity, so there's a need for an LTE
Dr.
antenna.
Sudhakar
So
Rao
there
should
are
know.
at least
You
4 to
please
5
send Esther's
antennas. Yes,
biodata
GPS for
to
tracking. There are 4 to
Professor
5 antennas, and
because
all the
as
antennas
Dr.
cannot be used
Sudhakar
all the
ended,
time, right? So
Indians
it
are
has to be
not second
reconfigured,
to
because if
none.
everything is used all the time, energy
Very recently
consumption,
only I
battery
saw
replacement,
Dr.
everything will become an
Esther's
issue. So,
biodata.
which is
Really,
why the design is very crucial. So miniaturization, size
Yes, sir.
reduction is extremely crucial. So just imagine the volume. If every person in a particular company and every such company is using this particular device, then energy consumption is so important. It is so crucial. So which is why wearable antennas, reconfigurable antennas, and several other antennas even, they play a very crucial role, especially with IoT evolving. So yes, that was about my presentation. Just to give you a brief summary. Firstly, we have seen about the wearable antennas, its design, and how it works under different situations, like on body, in bent situations, under crumpled situations, with wetness, and about the specific absorption rate. Following that, we saw about the reconfigurable antennas and the different methods with which we could achieve reconfiguration, and the classification of reconfigurable antennas and reconfigurable antennas in cognitive radio. And then we saw about IoT and how important are antennas, wearable antennas and other antennas in IoT, and we just
Yeah,
saw
I
a
think
simple flow system.
audio is not
And
working
since
properly.
I think we are running
Yeah,
short of
but
time, I think
very good
I'll
talk
just
and very
complete with this.
interesting.
Thank
Keep
you.
up
Thank you so
good
much.
work.
Thank you, sir. Thank you. Thank you. I'm so very happy
Hello?
to hear such words from such a great stalwart. Thank you, sir.
Hello, ma'am.
Very
Yes,
good.
yes.
Thank
Thank you,
you.
sir. Thank you. Thank you so much. Yes.
So with this,
presentation is not there.
we are winding up the session.
Yeah, 1 second.
So the next
Okay, ma'am.
session is scheduled at 1:30 p.m. Thank you, madam, for a very informative
Thank
session.
you. Thank you. Thank you so much, ma'am. Thank you. Okay, can you see?
Yes, ma'am.
Yes.
The slideshow, ma'am, slideshow.
Yeah. Yeah. Yes. Hello?
Hello, ma'am.
Yes.
Hello?
Yes, ma'am. Yes, ma'am.
Madam, I think Madam has completed and we can start the questions. Is it okay, ma'am?
Yes,
Yes.
sir.
Yeah,
We
yeah.
can.
Sir, we will be presenting now. Thank you, ma'am, for a very informative session. So we'll be
Thank
sharing
you.
the questions now.
Yeah.
Ma'am, the first question is from Dr. Sudhakar Rao.
Yeah.
Is it visible? The questions are visible?
Yes.
Okay.
Yeah. Yes, are you working in any industry on these things in India? Also, there are significant applications of RFID, and is there work done in India in this area? Yes, actually, I am working in a company called Invikara. So it's into building digital twin of a building, say for an airport, the digital twin. So they are getting into implementing even the RFID aspects also. Yes, significant applications of RFID are definitely there. Even for access control and things like that. So yes, there is work that is being done in India also. There are manufacturers of beacons with RFID. Yes, so that is about the answer for his question. Bending has effect on the polarization and radiation pattern of wearable antenna. How is it quantified? Yes, definitely. Bending has an effect on the polarization and radiation pattern. However, it has a major role to play with the fabrication. So it's important how durable we are fabricating. If we are using machine-based fabrication methods, then we can design a wearable antenna which is as good as a rigid, a normal antenna. So so if an antenna is built in a proper way, even when it is bent, there will not be much of a change. Probably there could be a few nulls. So it's for us to see if it would drastically affect our performance. But however, as far as I have seen, if the antenna is manufactured in a very proper, authentic way, there should not be much of a problem. And yes, is there any design of wearable antenna of 5G application in design perspective? How the effect of earth, ground, and environment on body-centric communication in the gigahertz band is addressed? Yes, there is wearable antenna for 5G applications also, and the effect of earth, ground, and environment on body-centric communications. Well, yes. So as far as the antenna is designed, so it is more
afternoon,
than the
Chandragopal
effect of
sir.
all these. It is the human body. The antenna is placed in close proximity to the human body, right? So it's the high dielectric constant of the human body which has a major effect on the antenna. So if that is addressed, if we are using structures like electromagnetic band gap structures and AMCs, then I think that itself will take care. There will not be much effect of the other parameters, environmental parameters. When the person says he is entering into a restricted zone, there's an alarm that goes in. Okay, and there's a microcontroller. There's a small storage unit. So everything is a part of this. Yes, but pin diode, because of the specific intrinsic region, this is just like pin identity card, which more suitable for higher frequency applications by everybody. And it is also there is an LED, evidently there is also an optional button. So it has the RFID. It's very evidently proven. RFID is for automated check-in. So RFID using the specific. That is the reason why we are going in for any employee can step in using the SAR will be estimated. Secondly, there is also the emanated wave from Wi-Fi. So there are different kinds of presses that can be programmed. The simulation, double press, the long simulation of SAR can be performed. Each press can be programmed in a different way. Say for example, a double press which will when a patient is wearing this particular and what is the role of reconfigurability? The information will immediately go to the nurse, and it will alert for an emergency situation, and she will come for a rescue. There are many. This is the kind of frequencies which are required in wearable applications, starting from GPS to kind of a use case workflow to LTE. Probably when there are so many frequencies involved, there is also a requirement for. And I think with this configuration, since the time is also so reconfigurability plays an important role in wearable antennas. As I had said, this is the is there a need to measure dielectric constant of textile every time and it's transmitting for the beacons designing, or can I use typical values? It's always typically it's better to make Eddystone and iBeacon package a measurement because constant intervals with a certain strength, right? So that is change from fabric to fabric. That is the same jean fabric which you get at a particular shop will have a slightly different value, a different thickness, a different he receives from the one you get in another shop. So it's always better to make a measurement before every design. He's pressing the button, which indicates the completion of any standard wearable antenna or a single press or a double press. It can be programmed accordingly. For user as a reference, this particular company does not manufacture wearable antennas. I have actually done research on wearable antennas, and I'm currently working in an IoT-based industry. From where it is received, we don't manufacture wearable antennas. So it will be able to store the information that this person is in conference room and he has completed his shift. Right now, everything goes. Any other questions? Okay. So now no when he presses the button, immediately the information goes to the cloud. Yes, this person has completed his shift and he is in this particular place. Right. So the cloud could be a public MQTT cloud or a private server. Okay, so every processing happens.
Good afternoon, sir.
Okay, so it's just a simple information in terms of bits and bytes which goes to the cloud, but it's the cloud which does all the processing. It will interact with various other servers. It interacts with the central. Okay, so it's from this particular place.
Has seen your biodata, there is a resume, and sir was so impressed and tell a good
this cloud will extract all the information. Thank you so much, sir. Thank you. I'm humbled and immediately it will send out an alarm to the next person who is in line to take over the shift. So the person who is in line to receive an alarm. So optionally, a text message also can be sent to the person who has to go and take over the shift, right? So he'll be sent like this person A has completed his shift, so you need to go to conference room X to take over the shift. So this is the process for this particular use case. So several other simple things like hospitality.
I want to tell Sangeeta Velan, your guide was my student.
Get something you want to do a particular service. Various other operations.
I think if I say Malati was your guide,
in COVID, post-COVID scenarios, so we are all very comfortably placed in a situation wherein we can afford to work from home. But there are not now, even before. There are people who cannot afford to work from home. They have to return back to work whatsoever.
But I am very proud.
There are food processing industries. There are pharmaceutical industries. There are emergency services wherein people have to return back to work.
Yes, sir.
The employees are the
certificate you can get.
How do we cater to those people? So
No, I
contact
learned
tracing
something today.
using
I think,
this particular
very good
technology
talk.
is very
Only thing,
very
part
much
of
important.
lecture I didn't hear
As you
because
can see,
I
a
went to
particular
some other
wearable device.
PhD
So wearable
student.
antennas are used in this particular
Anyway,
device. So
very
the
happy
wearable
to
antenna,
see
it needs to have an
you as well
RFID
as
for
great for
accessing to
sharing
it,
your
and
lecture.
it needs to have this Bluetooth low
Thanks
energy
to all.
2.4
Thanks to
gigahertz
all.
Bluetooth frequency,
I'm humbled.
Wi-Fi, and then
Thank you
it needs,
so much, sir.
suppose
Thank
the
you
person
to
is infected
Sudhakar Rao
and he's
sir,
sitting at
Raghavan
home
sir,
with a button
Perumal Shankar
pressed,
sir,
and it's really give
I'm
the information to
humbled.
the person who's
Thank
sitting
you
in
so
the
much, sir.
company and the
You please
server.
tell your
Then
friend Esther.
there's a need for an
Esther's
LTE
biodata.
connectivity, so there's a need for an LTE
Dr.
antenna.
Sudhakar
So
Rao
there
should
are
know.
at least 4
You
to
please
5
send Esther's
antennas.
biodata
GPS for
to
tracking. There are 4 to
Professor
5 antennas,
Sir,
and
because
all the
as
antennas
Dr.
cannot be used
Sudhakar
all the
ended,
time, right? So
Sir,
it
start
has
the
to be
session,
good,
sir.
because if everything
So,
is used all the time, energy
very
consumption,
recently
welcome
only I
back.
battery
Now we
usage,
are
and
entering
everything
the
will become an
Esther's
issue.
third
biodata.
technical
Which
session
is why
Really,
on the
the
topic
design is very
electromagnetic
crucial.
simulation
So
of 5G antenna with
miniaturization, size
CST
reduction is
MWS
extremely
by
crucial.
Mr.
So just
Chandragopal.
imagine the
Mr.
volume.
Chandragopal
If
is a
every
strong
person in a particular
engineering
company and
professional
every
with
such
a master's
company is
degree
using this
focused
particular
in
device, then
RF and
energy
microwave
consumption
from
is so
Indian
important.
Institute
It
of
is so crucial.
Technology,
So
Indian
which
School of
is why
Mines, Dhanbad.
wearable antennas,
He currently
reconfigurable
works
antennas, and
as
several other
CST
antennas
application
even, they
engineer
play a
in
very
Jyoti
crucial role,
Electronics
especially
and have
with IoT
expertise in
evolving.
higher
So
frequency applications
yes,
like
that was about
antennas,
my
metamaterials,
presentation. Just
circulator,
to give you
EMI,
a brief
EMC,
summary.
RCS, and particle
Firstly, we
dynamics.
have seen
The role of
the
CST
wearable
application
antennas,
engineer in
its design,
Jyoti Electronics
and
is providing
how it
technical
works
solutions to
under different
regulate government
situations, like on
organizations
body,
like
in vent
ISRO,
situations,
BAR,
under crumple situations with
RRCT,
wetness,
DRDO,
and about the
Bell
specific
IIT,
absorption rate.
NIT,
Following that, we
various
shall
private
complete with this.
And
Thank you.
keep up
Thank you so much. Thank you, sir. Thank you. Thank you. I'm so very happy to hear such words from such a great stalwart. Thank you, sir.
Ahmedabad,
Hello, ma'am.
Gujarat.
Yes,
So,
yes. Thank you, sir.
I will introduce
Thank you so
about
much.
us. Jyoti Electronics is a recognized techno trading house based in India, Ahmedabad, and we are serving the Indian marketing from last 35 years and diversified towards marketing of RF and house based in India, Ahmedabad, in 2000. And we are serving the Indian marketing from last 35 years and diversified towards marketing of RF and house, EMI and SIPI in 2000. So it's we are serving Indian marketing from last 35 years and diversified towards marketing of RF and house, EMI and SIPI in 2000. So it's we are serving Indian marketing from last 35 years and diversified marketing of solvers, EMI and solvers, and we are serving Indian marketing from last 35 years and diversified EMI and solvers, and we are serving Indian marketing from last 35 years and diversified EMI and solvers, and we are serving